Hello there, and welcome to Physics with William, where curiosity gets comfortable, and even the strangest corners of physics are given a little room to breathe. Tonight we are settling in with a topic that sounds at first like it ought to belong to a very stern textbook, and yet turns out to be one of the oddest and most important ideas in all of modern science. We are going to spend some time with the boson, that peculiar kind of particle which, unlike the rest of matter's crowded and fussy inhabitants, does not seem especially interested in personal space. If that sounds a bit rude, or at the very least socially unconventional, do not worry. In the quantum world, manners are rather different, and what looks like misbehaviour from our everyday point of view often turns out to be the reason the universe works at all. Before we get too far into that, I would love to know where in the world you are listening from tonight, and what sort of hour it is in your little corner of things. Are you hearing this late in the evening, when the day has finally stopped making demands of you? Or perhaps much earlier, while the house is still quiet and the kettle has only just begun to think about boiling? There is something fitting about talking about quantum particles while scattered across different rooms, different countries, different time zones, all arriving together in the same line of thought for a little while. And if you find this soothing, interesting, or simply a pleasant way to wind down while your brain gently pretends it is not still doing science before sleep, I would be grateful if you liked the video and subscribed. It helps this calm little corner reach other people who may also want something thoughtful and quiet at the end of a long day. Now then, let us ease our way into the story, because the boson is one of those ideas that first sounds small and technical, and then steadily grows until it seems to be quietly holding up half the known universe. The first thing to say is that a boson is not a single particle. It is a category, a kind of quantum citizen, a member of a larger family. That may sound less dramatic than it deserves, but categories matter a great deal in physics. A whale and a trout are both animals, but if one of them climbed a tree you would rightly suspect that something had gone badly wrong. In much the same way, particles come in different kinds, and the way they behave depends deeply on which kind they are. Bosons belong to one of the two great families of particles we use to describe nature. On the other side are fermions, and those are the particles that make up what we usually think of as matter. Electrons, quarks, protons, neutrons in their deeper structure, all of them belong to the more reserved and territorial branch of the particle family tree. Bosons, by contrast, are the less private sort. They are the particles associated with forces, with fields, with collective behaviour, and with some of the strangest large-scale effects in quantum physics. Light is made of bosons. The particle connected to the electromagnetic force is a boson. The particles involved in the strong force are bosons. The Higgs boson, famous for causing a great deal of excitement and a large amount of collider work, is of course a boson as well. Even before we define the term carefully, you can already sense that these things are not a minor footnote. They are everywhere, and they are doing essential work. Still, that does not quite answer the real question, which is what a boson actually is. If I place a chair in front of you, I can point to it. If I describe rain, you can picture the drops. If I say boson, the mind tends to produce a sort of vague, glowing pebble with an expensive scientific label attached. That is understandable, but not especially helpful. So let us begin with behaviour rather than appearance, because in quantum physics what something is and how it behaves are tied together very tightly. A boson is a particle that follows a particular set of quantum statistical rules. That phrase may sound dry enough to require a blanket and perhaps a stronger cup of tea, but it contains the whole heart of the matter. Bosons do not arrange themselves the way fermions do. Fermions are governed by a strict rule that says no two identical fermions can occupy the same quantum state at the same time. In plain language, if one identical fermion is already sitting in a certain quantum seat, another one cannot sit there too. It must find another seat. Bosons do not have this restriction. If a boson finds a quantum state already occupied by another identical boson, it does not recoil in horror and go looking for another arrangement. It is perfectly happy to join in. This, more than anything else, is why bosons are strange. They do not follow the rule that matter particles follow. They are not required to spread themselves out in that same exclusive way. In fact, under the right circumstances, they positively prefer to gather together. If fermions behave like very polite dinner guests who insist on individual chairs, Bosons behave more like concert goers who discover that one corner of the room has better acoustics and all wander over there at once. It is not chaos exactly, it is quantum preference. And once you understand that, a great many bizarre things start to make sense. To see why this matters, it helps to step away from the word boson for a moment and think about ordinary objects. In the everyday world, identity is straightforward enough. Two tennis balls may look the same, but we still imagine them as two separate things. One can sit on the table and the other roll under the sofa. We can track them, we can label them, we can feel that they each have their own little biographies, however modest. In quantum physics, identical particles are more deeply identical than that. They are not merely similar copies. They are fundamentally indistinguishable in a way that resists ordinary intuition. You do not get to tag one photon as Harold and another as Susan and then follow their private adventures through the apparatus. The theory simply does not work like that. When identical quantum particles trade places, nature responds differently depending on whether they are fermions or bosons. That difference, invisible in daily life, has enormous consequences. Bosons are the particles for which the overall quantum description stays in step when they are exchanged. That sounds very technical, but the practical result is simple. Their wave-like descriptions reinforce one another in a way that encourages bunching, sharing, and collective occupation. Bosons do not merely tolerate company. Under the right conditions, they form whole patterns of company. They pile into the same state, act in unison, and give rise to behaviours that look almost impossible when seen from the outside. Light is one of the clearest examples. Photons are bosons. When many photons occupy the same state in an organised way, you get laser light, a beam so orderly that it behaves very differently from the mixed and wandering light of an ordinary bulb. That is already a hint of the bosonic personality. Bosons can lock into shared behaviour. They can move in step. They can produce effects that are much more coordinated than anything we would expect from a random crowd of particles. It is worth pausing on that because it gets close to the deep reason bosons matter so much. The universe is not built only from little billiard balls bouncing independently about. It is also built from fields, from interactions, from large numbers of particles acting together, from patterns that emerge only because some quantum entities are willing to share the same arrangement. Bosons are central to that side of the story. Without them, the world would not simply be slightly different. It would be unrecognisable. You may wonder at this point why nature has such two sharply different temperaments available at all. Why should one family of particles insist on separation, while the other family is content with overlap? Why have a universe where some particles behave like guests guarding their place cards and others behave like they have all decided to form a choir? The honest answer is that this is how the quantum structure of reality appears to be built. At a deep level, these different behaviours are tied to another property called spin, which we will come to properly later on. For now, it is enough to say that bosons are not being rebellious or careless. They are obeying the rules exactly. They simply obey a different set of rules than the matter particles do. That distinction is important because the phrase does not follow the rules can sound as though bosons are somehow breaking physics, when in fact they are doing the opposite. They follow the rules that belong to bosons with complete obedience. What they do not follow are the rules that we, as creatures made of fermionic matter moving through a familiar world of separate objects and personal boundaries, might have expected them to follow. They fail to behave like the particles that make up chairs, lungs, bread, teacups, and tired people trying to understand quantum theory in bed, and that makes them feel peculiar to us. There is also a subtler reason bosons can be hard to grasp. Many of the bosons that matter most are not the sort you find sitting around as components of ordinary stuff. Electrons in atoms, those are easy enough to treat as matter-building blocks. Quarks inside protons and neutrons, same idea. But photons, gluons, the Higgs boson, These are not usually the particles people imagine when they picture what the world is made of. They are involved in carrying forces, shaping fields, enabling structure, creating mass relationships, binding things, transmitting influence. Their role is often more like activity than furniture, less brick, more message, less table leg, more the reason the table leg exists in a stable and meaningful way. That is why bosons can seem elusive. They are deeply real but not always intuitive in the same way that matter particles are. They are often associated with what happens between things rather than simply what things are. And in modern physics, that difference is absolutely central. The older picture of reality liked to imagine forces as rather abstract influences acting across space. Modern quantum field theory speaks a different language. In that language, interactions are described in terms of fields and the quanta of those fields. Those quanta very often are bosons. So when one electron repels another, when nuclei are held together, when light crosses a room and reaches your eye, bosons are in the story. Now, because this is the opening stretch of our journey, it is helpful not to rush straight into the entire machinery of quantum field theory, with all the delicacy of a lorry entering a greenhouse. Better to keep a close eye on the main point. A boson is a kind of quantum particle whose defining feature is that identical bosons can share the same quantum state. That one fact produces an astonishing range of consequences. It allows particles of light to bunch together. It allows certain atoms, when cooled to extremely low temperatures, to collapse into a shared quantum condition known as a Bose-Einstein condensate, where a whole cloud of atoms behaves almost like one giant matter wave. It helps explain superconductivity and superfluidity, those eerie states in which materials conduct electricity without resistance or flow without friction in ways that seem to ignore everyday common sense. Bosons do not merely sit in the catalogue of particles, they open the door to collective quantum life. There is something almost funny about that. We are taught from childhood that the basic lesson of physical objects is separateness. One apple is one apple. One marble is one marble. Put them together and you have a collection. But bosons challenge that picture. In the right circumstances, they do not behave like a collection of stubbornly separate little units. They behave like a coordinated whole. It is one of the first clues that the quantum world is not simply a smaller version of the visible world. It is arranged according to deeper principles, and those principles can make sameness far more powerful than separation. The history behind the word is also worth a moment of attention, because names in physics often carry the memory of how a strange idea entered human thought. The boson is named after Satyendra Nath Bose, an Indian physicist whose work on the statistics of photons helped open the way to this whole category of behaviour. Albert Einstein recognised the importance of Bose's approach and extended it, which is why you will later encounter the phrase Bose-Einstein statistics and the state of matter called a Bose-Einstein condensate. It is one of those lovely moments in science where a name is not decorative. It marks a real turning point in how nature was understood. Before Bose, physicists were already grappling with light, energy, and the increasingly undeniable fact that the microscopic world was not going to behave in a neat classical manner, just because people preferred it that way. Bose's insight into how photons should be counted was not a trivial accounting trick. It revealed that identical particles of this kind had to be treated differently from classical objects. And from that difference came an entire branch of quantum behaviour that still shapes cutting-edge physics now. Even so, if you had asked someone in the street what a boson was for most of history, they would have looked at you the way one looks at a person who may be about to explain string quartets using only potatoes. It is only in recent decades, and especially after the discovery of the Higgs boson, that the term began to drift into public awareness. Unfortunately, public awareness often arrives with a suitcase full of misunderstandings. Many people heard boson and assumed it meant rare, mysterious, and probably floating in a giant tunnel in Switzerland. The truth is at once less dramatic and more profound. Bosons are not unusual exceptions that physics occasionally wheels out for special occasions. They are woven into the ordinary functioning of the universe. Every beam of light is full of bosons. Every electromagnetic interaction involves bosonic behaviour. They are not hidden on the margins, they are active at the centre. Still, calling them active at the centre does not mean they're easy to picture. Quantum particles resist picturing for a living. They are not tiny grains in the old sense. They are excitations of fields, quanta of interaction, participants in a mathematical structure that does not map neatly onto the furniture of common sense. That is another reason this topic rewards patience. To understand a boson, you do not need to force it into the shape of a microscopic bead with a bad attitude. You need to think in terms of what nature permits, what kinds of states can be shared, and what large-scale consequences follow from those microscopic permissions. In a way, bosons teach a lesson that comes up again and again in modern physics. The deepest differences are not always differences of substance in the old material sense. They are differences of behaviour, symmetry, and allowed arrangement. What a thing is cannot always be separated from how it may exist among other things. Bosons are not defined by being shiny or forceful or especially glamorous. They are defined by the kind of collective life the quantum world allows them to have. And that takes us right to the edge of the next question, which is why the universe divides its particles this way at all, and what exactly it means to say that bosons do not follow the same rules as matter particles. Because once you start looking at bosons in contrast with fermions, the structure becomes much clearer. You begin to see why matter has solidity, why atoms stack themselves as they do, why light can be amplified into a laser, and why some particles build the world while others help govern the interactions that let the world function. The distinction is not academic. It is one of the main organising principles of the quantum universe, so for now it is enough to settle into the idea that a boson is a quantum particle defined not just by what it is called, but by how it behaves with others of its own kind. It does not obey the exclusion rule that keeps fermions apart. It can share, it can gather, it can reinforce, it can turn many into something that behaves almost like one. And that odd willingness to overlap, which sounds at first like a minor technical detail, is the beginning of some of the most important physics we know. In a moment, the contrast with the other great family of particles starts to sharpen, and once it does, the boson stops seeming like a strange word from the far end of a textbook and starts looking like one of the key answers to why reality has the texture it does. To make sense of why bosons are different, it helps to zoom out a little and look at the broader arrangement nature seems to prefer. For all the staggering variety in the universe, for all the stars and salt grains and dragonflies and radio signals and teaspoons and people standing in kitchens wondering whether they remembered to turn the oven off, the particle world underneath it all turns out to be organised in a surprisingly economical way. Modern physics sorts the basic quantum ingredients of reality into two great families, not 10, not 50, just two. Fermions and bosons. One family gives us the stuff that occupies space in the stubborn everyday sense. The other gives us much of the activity, the communication, and the strange collective behaviour that holds the whole performance together. At first, that may sound almost too tidy. Nature, after all, has a reputation for being unruly. It produces quasars, octopuses, weather systems, and whatever it is printer cables do when left alone in a drawer for more than 3 hours. But beneath the surface messiness, the rules are remarkably spare. And one of the deepest of those rules is that particles fall into one of these two camps. Once you begin to see what that means, an enormous number of things start lining up. Why matter has structure. Why atoms do not collapse into a miserable little heap. Why light behaves the way it does. Why some particles can gather into a single quantum state while others refuse to do anything of the kind. The distinction is not decorative, it is structural. The easiest place to begin is with matter, because matter is what we are most used to. If you rest your hand on a table, the reason your hand does not drift gently through the wood like a philosophical ghost having a difficult evening is tied to the behaviour of fermions. Fermions are the particles that build what we ordinarily call matter. Electrons are fermions, quarks are fermions. The protons and neutrons built from quarks function in the larger everyday story as matter particles too, though their internal details are more involved. These particles follow a rule that forces them to maintain a kind of quantum individuality. Identical fermions cannot all pile into the same state. They must spread out. That spreading out is one of the reasons matter has shape and stability. In atoms, electrons cannot all sit in the same lowest energy arrangement. If they could, every atom would be a much sadder and less interesting object. Instead, electrons stack into different levels and configurations. Chemistry becomes possible because of that arrangement. The periodic table exists because of that arrangement. Your bones, your lungs, the air around you, the mug on the table, all of it depends on fermions being unwilling to share a quantum seat with identical neighbours. Matter is spacious, layered, structured, and resistant, partly because fermions are, in a quantum sense, deeply territorial. Bosons do not behave like that. They belong to the other great family, and their difference begins right there. Identical bosons are allowed to occupy the same quantum state. More than that, they often have a tendency to do so. This is the point where the two families part company most dramatically. Fermions enforce distinction. Bosons permit overlap. Fermions create the architecture of matter by refusing to crowd together in identical ways. Bosons make possible an entirely different style of physical behaviour, one in which many particles can act in concert, sharing the same arrangement and reinforcing one another. This contrast is so central that physicists can often tell a great deal about a particle simply by knowing which family it belongs to. It is rather like learning whether an animal is a mammal or a bird. That alone does not tell you everything, but it immediately narrows the field of likely behaviour. A boson is not just another particle with a different name tag. It is a particle whose place in the logic of nature is different from the beginning. At the deep mathematical level, the distinction is tied to spin. Now, spin is one of those words in physics that sounds comfortingly familiar right up until you try to use it in a sentence and realise it has wandered away from common sense. It does not mean that particles are literally rotating little beads in space like tiny tops, though that image has misled generations of students with great enthusiasm. Spin is a built-in quantum property, a fundamental feature of particles rather than a description of little surfaces physically turning. Fermions have what are called half-integer spins. Bosons have integer spins. That difference, technical as it sounds, determines the statistical rules they follow. And those statistical rules are not small details. They shape the large-scale world. Particles with half-integer spin follow one statistical pattern, the fermionic one, and particles with integer spin follow the bosonic one. That is why the two families behave so differently. It is not a matter of taste or mood. A photon does not gather with other photons because it is feeling sociable that afternoon. It does so because it is a boson, and bosons obey the statistical structure attached to that kind of particle. In quantum physics, a small difference in category can become a gigantic difference in consequence. This is where the phrase "why" bosons are different begins to sharpen into something precise. Bosons are different because nature allows them a kind of shared existence that fermions are denied. They can accumulate in the same state, move coherently, and create large-scale quantum phenomena that simply do not happen in the same way with matter particles. A crowd of fermions becomes layered. A crowd of bosons can become unified. That contrast is one of the deepest patterns in modern science. Think for a moment about light. Light is made of photons, and photons are bosons. That means you can have enormous numbers of photons in the same state. In a laser, this is exactly what happens in a controlled way. The photons line up in frequency, direction, and phase, producing a beam of remarkable order. If photons were fermions, laser light as we know it would not exist. The photons would be forced apart into separate arrangements. The beam would lose the special coherence that makes a laser a laser. So even in one of the most familiar triumphs of modern technology, the bosonic nature of the photon is not a side note. It is the whole game. The same broad story appears in far stranger places too. Cool certain atoms to temperatures near absolute zero, and if those atoms behave effectively as bosons, they can enter a shared state in which the distinction between many particles begins to blur into a single macroscopic quantum condition. This is the Bose-Einstein condensate, one of the most remarkable states of matter ever produced in the laboratory. Instead of behaving like a gas of separate atoms darting about independently, the collection behaves more like one giant quantum object. It is almost impossible to overstate how odd this is from the everyday point of view. We spend our lives surrounded by collections that remain collections. Bosons, under the right conditions, can become something closer to a unified whole. None of that would happen with fermions under the same conditions. Fermions, because of their exclusion rule, resist such complete sharing. Even when fermions act collectively, as they do in many fascinating systems, they do so through a different route. They remain subject to the rule that keeps identical ones from occupying the same state. Bosons, by contrast, take the door marked together and walk through it without complaint. There is also a broad difference in the roles the two families tend to play in our standard picture of physics. Fermions are the matter particles. Bosons are often the force carriers. That statement is a little simplified, but it is a very good starting point. Electrons, quarks, neutrinos, these are fermions. Photons, gluons, the particles associated with the weak interaction, and the Higgs boson, these are bosons. So the family division is not only about how particles behave statistically, it is also reflected in what jobs they tend to do in the universe. This matter and force distinction should be handled carefully, because physics always punishes casual simplification eventually, usually when one starts to feel confident. Still, there is a genuine pattern here. Fermions tend to be the particles you think of as forming the contents of things. Bosons often mediate interactions or arise from fields in ways that govern how those contents behave. If fermions are the cast of characters on stage, bosons are often part of the lighting, the sound, the messages passed between actors, and in some cases the very rules that let the performance cohere at all. Photons carry the electromagnetic interaction. Gluons are involved in the strong interaction that binds quarks inside protons and neutrons. The weak interaction has its own bosons. The Higgs boson is associated with the Higgs field, which plays a central role in how certain particles acquire mass. So when physicists talk about bosons, they are often talking about the machinery of connection. Bosons help explain how things influence one another. They show up in the grammar of interaction. That gives bosons a slightly slippery reputation in the public imagination. Matter feels solid and intuitive. We like particles we can imagine as little building blocks. Bosons often sound more elusive because they're tied to forces and fields are not something we evolved to picture naturally. Nobody on the African savannah needed an instinctive mental image of a gauge boson to avoid being eaten by something with teeth. Natural selection had other priorities, so modern physics often demands conceptual habits our brains did not come prepared with, but the fact that bosons feel less intuitive does not make them less real. In fact, their reality shows up every time the world behaves the way it does. Every glimmer of light reaching your eyes involves bosonic physics. Every stable atom depends not just on fermions occupying orderly arrangements, but on electromagnetic interaction, which is described through the photon. The universe is not a heap of matter with a few optional extras sprinkled on top. It is a network of fields and interactions, and bosons are central to that network. It is also worth noticing that the division into two families helps explain why the world is not either too rigid or too shapeless. If everything behaved like fermions, the universe would be a very different place, packed with exclusion and layered separation. If everything behaved like bosons, identical particles would pile into shared states in ways that would erase much of the structure we take for granted. Nature seems to require both temperaments. One family enforces order through refusal. The other permits order through sharing. One gives us stable architecture. The other gives us communication, fields, and large-scale coherence. Between them, the complexity of the world becomes possible. There is something quietly elegant in that. The two families are not enemies. They are complementary. Matter needs interactions. Interactions need participants. Structure needs both resistance and coordination. You could say fermions make rooms and bosons carry messages through the halls. It is not a perfect metaphor, but it is close enough to be useful at this hour. The point is that the particle world is not divided into important things and decorative things. It is divided into different kinds of essential things. When students first meet this distinction, there is often a temptation to think of bosons as the weird ones, and fermions as the normal ones. That is understandable because we ourselves are made of fermionic matter arranged into very opinionated biological systems. We experience the world through solidity, location, boundaries, and exclusion. We sit in one chair, not several. We occupy one patch of mattress, give or take. So fermionic behaviour feels natural to us because it underlies the stable world of objects and bodies. Bosons seem odd, only because we are not built out of them in the same direct sense. From the universe's point of view, though, there is nothing especially normal about fermions and nothing especially outrageous about bosons. They are just two lawful modes of being. We happen to notice one as ordinary because it composes the visible furniture of our lives. The other often reveals itself more indirectly, through radiation, interaction, symmetry, and collective quantum effects. But indirect does not mean secondary. Some of the most powerful phenomena in nature are bosonic through and through. One subtlety here is worth keeping in view. Not every boson is a force carrier in the simple everyday sense. The Higgs boson, for example, occupies a special place. It is associated with a field that fills space, and its role is not identical to that of the photon. So while it is useful to say that bosons often mediate interactions, it is better to think of them more broadly as particles that belong to the bosonic category, with all the quantum permissions that category entails. The family resemblance matters more than any single job description. That family resemblance shows up beautifully in how bosons behave collectively. Give a set of identical bosons the chance to settle into the same state, and they can produce behaviour that looks almost engineered. This is one reason bosons are so important in condensed matter physics, low-temperature systems, and technologies that depend on coherence. Superconductivity, for instance, involves electrons, which are fermions, but under certain conditions they pair up in a way that makes the pairs behave effectively like bosons. Once that happens, the system can enter a shared quantum state that allows electrical current to flow without resistance. It is one of those delightful moments in physics where categories do not merely sit in textbooks. They reach out and govern what wires can do. So when we ask why bosons are different, the answer is not just that they are another item in the particle inventory. Their difference lies in the quantum social rules they obey, the kinds of states they can share, the roles they often play in interactions, and the large-scale phenomena they make possible. Fermions build the ladders. Bosons let whole groups stand on the same rung. Fermions define occupancy. Bosons make coherence possible. Fermions give us the grain of matter. Bosons give us light, mediation, and some of the most dramatic examples of nature behaving as one. There is another reason the two-family picture matters so much. It teaches us something about the limits of ordinary imagination. In daily life, we think individuality is basic, and collectivity is something added on later. We imagine separate things first and coordinated behaviour second. The quantum world is not always like that. In the bosonic case, collective occupation is built into the most fundamental rule set. The possibility of acting together is not an afterthought. It is native to the category. That should probably make us a little more cautious whenever we assume that the microscopic world must resemble tiny versions of our visible world. Very often it does not. Very often it has its own logic entirely. All of this may sound grand and a little remote, but it comes home in practical ways. Electronics, optics, particle physics, quantum technologies, material science, all of them rely on understanding which particles are fermions and which are bosons. This is not an elegant philosophical distinction kept alive mainly by professors with chalk dust on their sleeves. It is part of how we predict experiments, design devices, interpret data, and understand why matter and radiation behave as they do. And there is also, if we're being honest, something satisfyingly dramatic about the fact that the universe runs on such a fundamental divide. On one side, particles that insist on taking turns. On the other, particles that can all join the same arrangement. One family produces the layered world of matter. The other allows for fields, forces, and organized quantum crowds. It is rather like discovering that all music comes from two basic kinds of note behavior, one refusing to overlap and the other quite content to harmonize. Not a perfect analogy, but close enough to feel the scale of it. As the picture sharpens, the boson stops seeming like an isolated curiosity and starts looking like one half of a deep symmetry in nature's design. Not symmetry in the narrow decorative sense, but symmetry in the sense of a balanced conceptual architecture. Two families, two rule sets, two ways quantum identity can shape reality. Everything that follows about bosons, why they bunch together, why they can mediate interactions, why they lead to lasers and condensates, and some of the strangest states of matter ever observed, rests on this basic split. So the next step is to look more closely at that startling bosonic habit itself, the willingness of identical bosons to gather into the same state rather than keep politely apart. Because once you focus on that single feature and follow it patiently, you begin to see why bosons do not just differ from fermions in some abstract technical sense. They differ in a way that changes what the universe can do, and that peculiar absence of quantum personal space turns out to be far more important than it first sounds. By now, the contrast is beginning to take shape. On one side are the particles that build matter by keeping orderly quantum distance from one another. On the other are the particles that seem, from our point of view, to have never developed much interest in that sort of boundary at all. And that brings us to the trait that makes bosons feel so unusual the first time you really look at them. A boson is the kind of particle that does not insist on staying in its own separate quantum arrangement when another identical boson is already there. Quite the opposite, it can share that arrangement, it can join it. Under the right conditions, it is even more likely to do so. That is why I have called it the particle that refuses to keep its distance, not because it is charging about the universe with reckless enthusiasm, but because nature does not impose on it the same rule of exclusion that it imposes on fermions. The first thing to clear up is that this refusal of distance is not the same as ordinary attraction. Bosons are not necessarily pulling one another together in the way gravity pulls masses together, or magnetism draws certain poles toward each other. The strangeness runs deeper than that. It is built into the way identical bosons are counted and described in quantum theory. If two identical bosons can occupy the same state, then the mathematics of their combined description allows them to reinforce that shared arrangement rather than forbid it. The result is a tendency we often call bunching. Bosons bunch. They show up together more readily than classical little objects would. They behave as though being in step is not merely allowed, but statistically favoured. That may still sound slightly abstract, so it helps to slow down and ask what it really means to say two particles are in the same state. In everyday life, two things cannot be in the same place, doing the same thing at the same time without us immediately complaining that one of them must be on top of the other, or that we have counted badly. But in the quantum world, a state is not just a location. It is a full set of quantum properties, including things like momentum, energy, and other characteristics that define how the particle exists in that situation. Identical bosons can share such a state completely. They are not elbowing each other in a microscopic lift. They are described by a common quantum arrangement. This is one of those moments where ordinary imagination reaches for a solid object picture and then quietly has to let go of it. Bosons are not acting like billiard balls that have forgotten how matter works. They are not tiny marbles attempting an impossible parking maneuver. They are quantum entities whose allowed descriptions permit overlap in a way that matter particles do not. If you picture them too classically, The whole thing becomes absurd. If you think of them as field quanta, whose behaviour is governed by different statistical rules, the absurdity turns into structure. Photons are the easiest way into this because light is both familiar and deeply weird, which makes it excellent teaching material. A photon is a boson. If photons behaved like fermions, you could not pile many of them into the same state. But they do behave like bosons, which is why light can be bright in the way it is. It is why a beam can contain huge numbers of photons sharing a common direction and frequency. It is why laser light is possible. A laser is not just a strong torch, it is a coordinated population of photons occupying the same state in a highly organised way. They move together, so to speak. They act less like a random crowd and more like a disciplined group that has somehow agreed on the route, the pace, and the exact same destination. That coordination is one of the clearest large-scale signs that bosons do not keep their distance. They are able to do the same quantum thing together. Once you see that, the bosonic personality stops feeling like an obscure technicality and starts looking like a major principle. The difference between particles that must spread out and particles that can pile in changes what reality can be. It affects radiation. It affects matter under extreme conditions. It affects technology. It affects the very idea of whether a quantum system behaves as a collection of separate occupants or as a shared whole. There is a famous experimental illustration of bosonic bunching that makes the point rather beautifully. Imagine sending two identical photons toward a device that can split their paths, something that would classically give each photon an even chance of going one way or the other. If these were ordinary classical particles, you would expect a fair number of cases where one goes one way and one goes the other. But identical photons do something stranger. Because they are bosons, the possibilities in which they leave by different routes can cancel in such a way that the photons prefer to leave together by the same route. They bunch. They stick with one another. It is one of those results that sounds almost like a prank played by the universe on common sense, except the experiment works. The particles are not communicating in the everyday way. They are obeying the quantum rules for identical bosons, and those rules make togetherness more likely than our classical instincts would predict. That example matters because it shows that bosonic closeness is not just a metaphor, it is measurable. It appears in interference patterns, in counting statistics, in the outcomes of carefully designed experiments. It is not that physicists stared at equations long enough to become sentimental about particles getting along. Nature itself displays the tendency. Bosons really do exhibit behaviour that favours common occupation and coordinated outcomes. Now, if you listen carefully to the way this is often explained, there is a hidden trap. People will say that bosons like to be together. That is useful language up to a point, but it can also mislead. Bosons do not have feelings, preferences, or a group chat where they plan to meet near the lower energy state because the acoustics are better there. What we mean is that the quantum statistics of identical bosons lead to enhanced probability for shared occupation. It is a lawful effect, not a mood. Still, one is allowed a little gentle anthropomorphism now and then, provided one does not start imagining photons arranging dinner parties. The contrast with fermions becomes even sharper here. Fermions are governed by exclusion. Identical fermions cannot occupy the same state. That is why electrons in atoms fill different levels instead of collapsing into one. Bosons face no such prohibition. So if a collection of bosons is allowed to settle and cool and lose the distractions that normally keep particles acting independently, they can accumulate in the same state in extraordinary numbers. When that happens, the system can cross a line from being many particles to behaving like one macroscopic quantum entity. This is not science fiction, and it is not a figure of speech. It has been achieved in laboratories with dilute gases cooled to unimaginably low temperatures. In those conditions, a set of bosonic atoms can form what is called a Bose-Einstein condensate. The name sounds formal and slightly chilly, which is fitting because the temperatures involved are so low that ordinary thermal motion no longer dominates. What emerges is a state in which an enormous number of atoms share the same quantum state. Instead of each atom behaving as a separate little individual, the whole ensemble begins to act coherently. It is as if many instruments that had all been tuning independently suddenly lock into one sustained note. Again, not because they have agreed on anything, but because the bosonic rules allow shared occupancy on a scale large enough for us to observe directly. That is a remarkable fact. The everyday world teaches separation. Bosons, under the right circumstances, teach unity. Matter as we know it is full of objects defined by boundaries. Bosonic systems can become defined by commonality. The underlying lesson is that individuality is not always the most basic story nature tells. Sometimes the deeper story is about collective state, shared configuration, and coherence. This is one reason bosons show up so often when physics reaches its strangest and most elegant effects. Superfluidity, for example, involves a liquid flowing with effectively no viscosity under special conditions. It behaves in ways that seem almost insolent toward ordinary friction. Superconductivity allows electric current to move without resistance. In that case, the story is a little more subtle because electrons are fermions, but under the right conditions they pair up into combined states that behave effectively like bosons. Once that happens, the door to shared occupation opens and the system can enter a coherent state that no collection of isolated fermions could achieve on its own. So even when bosons are not sitting there as the original ingredients, bosonic behaviour often appears as the root to the phenomenon. There is also a useful point to make about scale. Bosonic effects are not always obvious in daily life, because thermal disorder tends to scramble delicate quantum coordination. At room temperature, with particles jostling and exchanging energy all over the place, the neat shared behaviour bosons are capable of is often washed out. That is why so many striking bosonic phenomena reveal themselves in carefully controlled conditions, intense radiation fields, or very low temperatures. The refusal to keep distance is always part of the rulebook, but you do not always get to see its full consequences unless the environment stops interrupting every 5 seconds. Even so, one bosonic effect is around you all the time, namely light itself. The brightness of a lamp, the beam of a laser pointer, the sunlight through a window, all of these involve enormous populations of photons, and because photons are bosons, they can accumulate in the same state in a way that gives light its particular quantum character. If photons were forced apart like fermions, the whole optical structure of the world would be different. So the bosonic habit of not keeping distance is not some remote specialty of cryogenic laboratories. It is built into the fact that the room is visible. Another subtle feature of bosonic closeness is that it is tied to indistinguishability. Classical particles can be labelled. You can imagine swapping them and still keeping track of which was which. Identical bosons do not permit that sort of bookkeeping in the same way. Their identity is deeper than resemblance. They are fundamentally indistinguishable members of the same quantum field. This matters because the very act of exchanging them does not create a new physical situation of the classical kind. That is part of why the shared description works as it does. Bosonic togetherness is not simply about proximity, it is about the structure of identity in the quantum world. If that sounds slippery, it is because it is. The quantum world is not obliged to preserve our favourite categories from the visible world. We like to think in terms of separate objects with individual histories. Bosons remind us that the deepest layer of nature often prefers a different language, one built from states, symmetries, and allowed combinations. Once identical bosons enter the picture, counting becomes stranger, possibility becomes structured differently, and the outcome is behaviour that would look almost impossible if we insisted on classical metaphors all the way down. At this point, it is tempting to say that bosons are sociable and fermions are antisocial, but that is probably unfair to both families. Bosons are not friendly. Fermions are not rude. Nature is simply partitioned into two kinds of statistical behaviour, and one of them allows crowding while the other forbids it. The result, however, is hard to miss. Bosons create a world in which togetherness is a legitimate quantum strategy. Fermions create a world in which separation is mandatory. We happen to live at the meeting point of both, where stable matter and interacting fields combine into stars, chemistry, weather, and the ongoing mystery of why socks continue to disappear in households that otherwise appear to obey physical law. There is something almost philosophical hiding in this, though it is really physics from start to finish. We often imagine that difference is what gives structure to the world. Bosons suggest that sameness can also give structure, provided the rules permit it. A crowd of bosons all sharing the same state is not a collapse into nothingness, it is a new kind of order. Coherence itself becomes the phenomenon. A laser beam is not dull because its photons are alike. It is powerful because of that alignment. A condensate is not less interesting because the atoms share one state. It is more interesting because a whole new scale of behaviour emerges once they do. That emerging coherence is going to matter a great deal as we continue, because the next issue is not simply that bosons bunch, but why the rules are built this way in the first place. What is it about bosons at the deepest level that allows this shared existence? Why should integer spin lead to one kind of statistical world and half integer spin to another? Why does nature attach togetherness to one family and enforce spacing to the other? Those are the questions that start to bring us from description into explanation, and once we step there, the boson stops being merely the particle that refuses to keep its distance and becomes a clue to the deeper logic of quantum law itself. What makes bosons seem so strange is not that they ignore physics, it is that they obey a part of physics that does not match our everyday instincts. When people first hear that identical bosons can gather in the same quantum state, while identical fermions cannot, it is very tempting to think the bosons are somehow breaking the proper order of things. We look at the solid world around us, where objects exclude one another, where one person cannot sit in exactly the same chair, in exactly the same way as another person at the same time, and we quietly assume that this must be the normal template for reality. Then bosons arrive and behave as though that assumption was never agreed upon in the first place. So when we ask why bosons do not follow the usual rules, the first answer is that the so-called usual rules are only usual from the point of view of matter like us. We are made from fermions arranged into atoms and molecules and living tissue. The visible world of tables and lungs and raindrops and bread crust is shaped very strongly by fermionic exclusion. That makes exclusion feel normal. It makes spacing feel basic. It makes individuality seem built into the foundation of things. But this is partly a matter of perspective. The universe does not begin by declaring that all particles must keep politely apart and then adding a strange exception for bosons. It begins with two lawful families, each with its own statistical behaviour. We simply notice one of those families more directly, because it builds the sort of matter we bump into with our knees. The deeper reason bosons behave differently lies in the structure of quantum theory itself. Once particles are truly identical, and once the world is described in quantum terms rather than classical ones, the idea of swapping two particles becomes more subtle than it first appears. In classical thinking, if you swap two identical marbles, you may not care very much, but you can still imagine that a swap has taken place. One marble was here and the other was there, and now they have traded places. Quantum theory treats that situation in a much more serious way. If the particles are genuinely identical, then the theory must reflect the fact that exchanging them cannot produce an entirely different physical world. The description of the system must remain consistent with their indistinguishability. That consistency can happen in two basic ways. In one case, swapping the particles leaves the overall quantum description unchanged in a way that supports shared occupation. That is the bosonic case. In the other, swapping them introduces the kind of structure that leads to exclusion. That is the fermionic case. Those are the two options nature provides. So bosons do not fail to follow the rules. They follow one of the two deepest rule sets available for identical quantum particles. This is where the matter becomes more technical, but it can still be understood without getting buried in formalism. In quantum mechanics, a physical system is described by something that carries information about the possible states of the system, and the likelihood of different outcomes. For identical particles, that description must behave in a consistent way when the particles are exchanged. Bosons are associated with a description that is symmetric under exchange. Fermions are associated with one that is anti-symmetric under exchange. Those words sound formidable, but their practical consequences are what matter. Symmetry for bosons means that placing one identical boson where another already is does not create a contradiction. Anti-symmetry for fermions means that trying to do the same thing collapses the possibility. That is the origin of the exclusion rule. So in a sense, the difference comes from the way quantum identity works. Bosons are not rebellious little particles with no respect for proper spacing. They are particles whose quantum descriptions combine in a way that allows overlap. Fermions are particles whose descriptions combine in a way that forbids identical overlap. The rules are not added later by hand. They arise from the form the theory is allowed to take if it is going to describe identical particles consistently. This may raise the next obvious question, which is why nature allows these two cases and not some wider menu of possibilities. That question leads toward one of the most important results in modern physics, the connection between spin and statistics. Bosons have integer spin, fermions have half-integer spin, and for reasons that go deep into relativistic quantum field theory, particles with integer spin must behave bosonically, while particles with half-integer spin must behave fermionically. This is not a casual correlation. It is one of the strongest structural links in theoretical physics. Now spin, as we touched on before, is not literal spinning in the ordinary mechanical sense. It is a built-in quantum property, part of what a particle is. And yet this strange property turns out to determine how large groups of identical particles can be arranged. That is one of the great lessons of modern physics. The universe is not assembled from separate lists of properties that never speak to one another. The character of a particle and the statistical rules it follows are deeply linked. Change one, and you change the world that particle can help produce. The full proof of the spin statistics connection is not something one casually brings out between supper and sleep, mostly because it takes serious machinery and a good deal of patience. But the broad idea can be stated plainly enough. If you want a theory that respects the requirements of relativity, that preserves causality, and that behaves consistently when fields are quantized, then integer spin particles and half-integer spin particles must fall into different statistical classes. Bosons emerge from that demand as naturally as fermions do. It is not that physics discovered bosons behaving strangely and shrugged. It is that the entire framework of quantum field theory points toward exactly this division. That is one reason the phrase usual rules needs careful handling. In ordinary conversation, the usual rules mean the rules we are used to. In physics, the usual rules are the ones that arise from the structure of the theory. Bosons are unusual only to human intuition. To the equations of the quantum world, they are entirely expected. And if anything, it would be much stranger if all particles behaved like fermions, because then light, force mediation, and coherent radiation would have no place to live in the theory we actually observe. Still, it is understandable that bosons feel like the odd family. Fermionic behavior produces the world of separate matter, and separate matter is what our senses evolved to manage. If a large predator is coming toward you, it is quite useful to perceive it as a distinct object occupying a distinct position, rather than as an excitation of underlying fields with category-dependent exchange properties. Evolution had its priorities, and advanced quantum interpretation did not make the shortlist. So the human mind defaults to a world of boundaries and separate occupants. Bosons challenge that by showing that at the microscopic level, shared existence is just as lawful as separation. Another way to understand why bosons do not follow the rules we expect is to notice how much of our expectation is shaped by crowding in the visible world. Put too many people in a lift and someone becomes unhappy. Try to stack too many physical objects into the same place, and the result is usually either a mess or a visit from a structural engineer. We are used to matter as something extended, resistant, and exclusionary. Bosons are not classical lumps of matter, so those intuitions do not apply. A photon is not a tiny pellet of yellowish light trying to squeeze into an already occupied slot. It is a quantum of the electromagnetic field. Its bosonic nature means that many such quanta can occupy the same state of that field. Once you think in terms of fields rather than little hard pellets, the strangeness begins to relax. Not vanish, perhaps, but at least stop looking like a disciplinary problem. In fact, the field picture helps a great deal. Modern physics does not think of particles as independent miniature objects first, and field behaviour second. It thinks in terms of fields as fundamental, with particles appearing as quantized excitations of those fields. A boson is then not merely a particle among particles. It is a quantum excitation associated with a field whose allowed occupation rules are bosonic. That is why large numbers of photons can occupy the same electromagnetic mode. That is why coherent light exists. That is why force-carrying fields can behave the way they do. Bosons fit the field framework beautifully. They are not exceptions living at the edge of the theory. They are central residents. There is also an important conceptual shift here. In classical thinking, order often comes from separation. Different objects occupy different places, perform different roles, and stay out of each other's way. In bosonic systems, order can come from sameness. Large numbers of particles in the same state do not create chaos. They can create extraordinary coherence. Laser light is orderly because the photons are aligned. A Bose-Einstein condensate is remarkable because many atoms share one state. Bosons reveal that nature has more than one way to build order. That is one reason they seem to violate the usual rules. They replace the familiar logic of orderly spacing with a less familiar logic of orderly overlap. It is worth stressing that this overlap is not a vague hand-waving idea. It shows up in measurable phenomena. Bosonic bunching has been observed directly. Photons display it in carefully designed optical experiments. At low temperatures, bosonic atoms display it in condensed systems. Superconductivity relies on effective bosonic behavior at a crucial stage. These are not poetic descriptions added later by science communicators looking for a quiet evening. They are real physical effects. The rules bosons follow are visible in the laboratory. At the same time, bosonic behavior does not mean all bosons simply collapse into one state whenever they get the chance. Conditions matter. Temperature matters, available states matter, interactions matter. A room full of ordinary light is not automatically a perfect laser. A gas of bosonic atoms at everyday conditions is not automatically a condensate. The rule is that bosons are allowed to share a state, not that they must do so under every circumstance. But when the situation is right, that permission changes everything. Fermions can never cross that line in the same direct way. Bosons can, and often do. There is a mild irony here that physics seems to enjoy. The particles that make up solid matter are the ones that insist on distinct occupancy. The particles that often mediate forces and radiation are the ones that can bunch together. So what feels solid and real to us is built from quantum refusal, while what feels intangible, like light and fields, often arises from quantum sharing. The world is stitched together by both temperaments at once. Matter gives it persistence. Bosons give it connection, transmission, and coherence. This also helps explain why bosons are so important in theories of interaction. A force-carrying particle must be able to show up in ways that permit fields to build up, waves to propagate, and large-scale effects to emerge. Bosonic statistics are perfectly suited to that kind of role. The photon does not get blocked from joining an electromagnetic field mode because another photon is already there. Gluons do not obey fermionic exclusion. The weak interaction bosons follow their own bosonic rules as well. The family resemblance is not accidental. The jobs these particles perform in nature fit their statistical character. And then there is the Higgs boson, which has a somewhat different reputation, but belongs squarely in the same family. The Higgs field fills space, and its associated boson reflects the same broad bosonic logic. even though its role is not simply that of a familiar force carrier in the popular sense. The important thing is that the bosonic category is not a narrow special case invented just for photons. It stretches across some of the most basic ingredients of modern particle physics. The more one looks, the clearer it becomes that bosons do not sit outside the rules. They define one whole side of them. You can also approach the question from the other direction. Suppose bosons did follow the rules we usually imagine, the fermionic-style rules of exclusion and separation. What would happen? Light would not behave as it does. Coherent radiation would be radically altered. The architecture of force mediation in quantum field theory would not look remotely the same. The large-scale quantum states that depend on shared occupation would disappear. Much of condensed matter physics would need to be rewritten from the ground up, assuming anything like our world survived the attempt. In other words, bosons do not follow the usual rules because the universe needs a category of particle that does not, and everything we observe confirms that such a category is real. Perhaps the most useful way to frame it is this. There are two notions of usual here. One is the usual of daily life, shaped by matter, boundaries, and common sense. The other is the usual of fundamental theory, shaped by quantum consistency, indistinguishability, spin, and relativity. Bosons violate the first notion and fulfill the second. That is why they feel so strange at first and so inevitable once you have sat with them long enough. The discomfort is ours, not theirs. Even the phrase refuses to keep its distance can now be heard more precisely. A boson does not keep its distance because the quantum world does not require it to. Its identity is not classical identity. Its occupation rules are not fermionic occupation rules. Its spin places it in a family that can share states, reinforce occupation, and under the right conditions generate collective phenomena of startling clarity. It is not ignoring order. It is participating in a different kind of order. That idea becomes especially important when we move from the abstract question of rules to the concrete question of what bosons actually do. Once you understand why they can gather, the next natural step is to ask what that gathering enables in practice. How does a bosonic particle act as a messenger of force? How does light emerge from bosonic behavior? Why do photons, gluons, and their relatives occupy such a central place in the modern picture of nature? The answer to that begins with the quiet work of exchange, because the particles that seem least like the furniture of the world often turn out to be the ones carrying its conversations. That brings us to one of the most important turns in the whole story, because once bosons stop looking like odd particles that enjoy sharing states and start looking like the carriers of interaction itself, the universe changes shape in your mind. Matter is no longer just sitting there with its properties sealed inside it like a box with the lid nailed down. Instead, matter is constantly engaged in exchange. It interacts, it responds, it pulls, pushes, binds, emits, absorbs, scatters, radiates, and in every one of those verbs there is a deeper layer of physics quietly at work. The bosons in that layer are not always obvious, and they are not always easy to picture, but they are essential. If fermions give us much of the cast of the material world, bosons often carry the messages that let the cast influence one another at all. The easiest place to begin is with light, because light is both familiar and deeply misleading in exactly the right way. We think we know what light is. It fills rooms, casts shadows, makes mornings look hopeful, and kitchens look less alarming, and generally behaves like one of the more cooperative features of reality. But the closer physics looked, the less simple light became. At times it behaves like a wave spreading out, interfering with itself, diffracting through narrow openings in a manner that seems too smooth and too graceful to belong to anything like particles. At other times it behaves as though it arrives in distinct packets, little quanta of energy that can be emitted or absorbed individually. Modern physics resolved this not by choosing one story and discarding the other, but by accepting that light belongs to the quantum world, where neat classical categories tend to loosen their collars and behave less rigidly. The particle associated with light is the photon, and the photon is a boson. That matters immediately, because it means large numbers of photons can occupy the same state. It means light can build up coherently. It means beams can become organized in ways that would be impossible if photons had fermionic habits. But the photon is not only important because it helps us understand light as a quantum phenomenon. It is also the boson associated with the electromagnetic interaction, and that is a much larger claim. It means that the same thing we experience as light is connected, at a deeper level, to the force that makes electrons repel each other, that holds atoms together through attraction between opposite charges, that drives chemistry, electronics, and a good deal of the visible structure of ordinary matter. This is where the quiet work of exchange enters the picture. In modern physics, forces are not treated simply as invisible influences reaching mysteriously across empty space in the old style. Instead, interactions are described in terms of fields and the quanta of those fields. When charged particles affect one another electromagnetically, the language of quantum field theory describes that interaction through the exchange of photons. Now, if that sounds as though tiny balls of light are being thrown back and forth between particles like notes passed in a classroom, it is worth being cautious. The everyday image is not entirely wrong as a first stepping stone, but it can become too literal very quickly. What matters is not the cartoon picture of one particle lobbing a neat glowing object toward another. What matters is that the electromagnetic field is quantized, and its quanta are photons. The interaction is described through that field and its allowed excitations. Still, even a careful approximation can be useful. Suppose you imagine two electrons approaching one another. They repel. That part is familiar enough. But what does it mean to say they repel? In the old language, one might say each electron has charge, and that charge somehow causes a force on the other. In the quantum language, the story becomes more structured. The electromagnetic interaction between them is described through the exchange associated with the photon field. The repulsion is not magic. It is not action at a distance in the old mysterious sense. It is the result of an interaction encoded in the field structure of nature itself. This way of thinking takes a little adjustment because we are used to treating light and force as separate topics. One seems visible and graceful. The other sounds like something from a diagram with arrows in a textbook. But in quantum electrodynamics, they are profoundly linked. The photon is not only the particle of visible light, it is also the mediator of the electromagnetic interaction in general, including cases where no visible glow appears at all. A light bulb shining across the room and an electron being deflected in an atom belong to the same deep framework. The same bosonic field is involved. The same particle category sits underneath both. There is something rather satisfying in that. Nature often turns out to be simpler in its foundations than in its appearances. What looks like many separate phenomena can be different faces of one structure. Light, magnetism, electricity, radiation, charge-particle interaction. These are not isolated subjects stapled awkwardly together by human naming conventions. They are aspects of the electromagnetic field, and the photon is its bosonic quantum. Of course, once one says the word exchange, another question follows quite naturally. If bosons are exchanged, does that mean force is always a matter of particles bouncing around like microscopic couriers? The answer is yes and no, which is the sort of answer physics gives whenever it is trying to be precise and frustrating at the same time. The particle description is real and indispensable, but it sits inside a broader field description. A field is not just a warehouse full of particles waiting to be thrown. It is a fundamental entity in its own right. Its quantum excitations are particles, and interactions are described through the behavior of those fields. So when we say a force is mediated by bosons, we are not replacing one crude mechanical picture with another. We are moving into a framework where fields and their quanta together describe how influence is transmitted. That is especially important because not every boson in such an interaction is something you can simply detect as an ordinary free particle in the same way you detect a beam of light. The full quantum description often involves what physicists call intermediate or virtual processes, and here the language can become slippery very quickly. These are not particles in the plain old everyday sense of little beads flying from one place to another and arriving in a detector with a boarding pass and a suitcase. They are part of the internal mathematical structure by which interactions are described. This is worth mentioning because popular explanations sometimes make it sound as though every force is just a visible exchange of tiny messenger pellets, and that is not really the right level of care. Better to say that bosonic fields mediate the interaction, and that their quanta are central to how the theory represents that mediation. Even with that caution, the basic idea remains powerful. Bosons often sit in the role of messengers, though messenger may be slightly too human a word. They are not deciding anything. They are not carrying opinions from one electron to another, but they are the quanta through which fields produce interactions. That is why bosons are so often associated with force. Their statistical nature, their relation to fields, and their ability to occupy shared states all fit beautifully into a universe where influence is not an abstract push from nowhere, but something woven into the quantum structure of space and matter. The photon is only the beginning. The strong interaction, the one that binds quarks together inside protons and neutrons and helps keep atomic nuclei from flying apart under electromagnetic repulsion, is associated with another set of bosons called gluons. Even the name sounds industrious, and for once the name is rather apt. Gluons are the bosons associated with the strong force, and they play the crucial role in holding quarks together. Without them, protons and neutrons would not have the form they do, and the nuclei of atoms would not be what they are. Matter at its most basic composite level would come apart before chemistry had the chance to start feeling pleased with itself. The strong interaction is stranger than the electromagnetic one in several ways. Gluons do not merely pass messages between passive participants. They themselves carry the type of charge relevant to the strong interaction, which means they can interact with one another as well. Photons do not do this in the same direct way under ordinary circumstances because they do not carry electric charge. Gluons, by contrast, belong to a more self-involved and complicated field structure. The result is a force that behaves very differently from electromagnetism. It becomes stronger in some contexts rather than weaker, and it leads to the remarkable confinement of quarks, meaning quarks are not found wandering freely through the world the way electrons can be. They remain bound into composite particles, and once again, bosons are at the centre of the story, not as decorative additions but as the very means by which the interaction exists. Then there are the bosons associated with the weak interaction, a force whose name sounds slightly apologetic until you discover what it actually does. The weak interaction is involved in certain forms of radioactive decay and in processes crucial to the behaviour of stars and to the production of elements. It is not weak in the sense of being unimportant. It is weak in a more technical comparative sense, and like many things in physics, the humble name conceals a very consequential role. The bosons associated with the weak interaction are massive, which gives the force a very short range. That matters enormously. The electromagnetic force can reach across large distances. The weak interaction is much more local in its effective reach. Once again, the nature of the bosons involved shapes what the force is like in the world. You can already see the pattern. Different interactions are associated with different bosonic fields. The properties of the bosons help determine the character of the force. If the boson is massless, as the photon is, the interaction can have long-range effects. If the boson is massive, the interaction tends to be shorter range. If the boson can interact strongly with itself, the force behaves differently than one in which the mediator remains more aloof. Bosons are not just labels attached after the fact. They are part of the reason forces have the personalities they do. And this is where the subject becomes quietly beautiful. We often imagine forces as abstract verbs: attraction, repulsion, binding, decay. But in the quantum world, those verbs are grounded in entities and structures. Light is not separate from electromagnetism. The photon ties them together. Nuclear binding is not just a general tendency to stick. It emerges from specific bosonic interactions at the level of quarks and fields. Even the processes that allow one kind of particle to transform into another in radioactive events depend on bosonic mediation. The universe is not held together by vague influence. It is organized by quantized fields whose bosons do real work. There is a temptation at this stage to think of bosons as secondary, because they often act between the matter particles rather than as the matter particles themselves. But that is a mistake, rather like thinking that language is secondary to people because it is used between them. Interaction is not an extra. It is part of what makes a world into a world. Matter without interaction would be a kind of silent inventory, a list without a story. Bosons help provide the story. They permit structure, transmission, coherence, change, and response. They are involved in why atoms exist, why light travels, why nuclei hold together, and why the universe is not a mute scatter of isolated ingredients. This also explains why bosons so often appear in the framework of gauge theories, which are among the deepest organizing ideas in modern particle physics. A gauge theory describes interactions through symmetries and associated fields, and the bosons that emerge in these theories are not optional decorations. They are required by the mathematical and physical structure of the theory. In other words, bosons are not being pasted onto force as a metaphor. They arise because the world seems to respect certain symmetry principles, and those principles naturally bring along field quanta with bosonic character. The photon in electromagnetism, the gluons in the strong interaction, the weak bosons in the weak interaction, all of them fit into that broader architecture. Now, none of this means every force in the most familiar list is handled exactly the same way in our present best theories. Gravity remains the particularly dramatic dinner guest in the room, because while many physicists expect a bosonic particle called the graviton in a fully quantized description of gravity, such a particle has not been directly observed. General relativity, our best theory of gravity at large scales, speaks a different language from the quantum field theories of the other interactions. So one must be careful not to talk as though the whole matter is tidily wrapped and stacked on the shelf. Physics is still working on some of its deepest unifications. Even so, for the interactions we understand best in quantum field terms, bosons are central mediators. It is also worth noticing how perfectly bosons suit this role. Their ability to share states allows fields like light to build into coherent waves and intense beams. Their connection to symmetry and quantized fields makes them natural carriers of interaction. Their properties shape the range and nature of forces. Matter particles may occupy the spotlight in the everyday imagination because they seem more object-like, but bosons are the ones making much of the stage machinery function. This becomes even more striking when one thinks about how little of the world would make sense without exchange. An atom is not just a nucleus with some electrons circling in neat little obedience, whatever old textbooks may have implied. It is a quantum system held together by electromagnetic interaction. Molecules form because electromagnetic forces shape the sharing and arrangement of electrons. Chemistry works because charges interact in structured ways. Your nerves signal through electromagnetic processes. Your eyes respond to photons. Metals conduct because electrons move within electromagnetic constraints. The visible world is not merely made of matter. It is animated, organized, and held in relation by fields and their bosons. And then, just when the boson seems fully established as a messenger, the story widens again. Some bosons do not merely carry familiar forces between particles. Some are tied to fields that fill space itself in a more pervasive way. The most famous example is the Higgs boson, associated with the Higgs field. The Higgs field is not simply a line of communication between isolated objects in the same style as a photon exchange between charges. It is a background presence throughout space, and particles interacting with it acquire important properties, most notably mass in the case of several fundamental particles. The bosonic family, in other words, does not only transmit interaction in the narrow sense, It also includes the quanta of fields that shape the very character of particles moving through the universe. That matters because it keeps us from turning bosons into one narrow idea. They are not just message carriers wearing bright uniforms and jogging between fermions. They are the quanta of fields, and those fields can mediate forces, organize interactions, and in some cases set the conditions under which particles possess the properties they do. Bosons are the language of connection in a very broad sense. So when we speak of light, force, and exchange, we are really circling around a larger insight. The quantum world is relational. It is built not only from things, but from the structured ways things can affect one another. Bosons inhabit that relational layer. They are often less visible to common sense than matter particles, yet no less real. They do not always announce themselves with the drama of a collision or the rarity of a headline-making discovery. Much of their work is quiet. A photon carries electromagnetic interaction. A gluon helps bind quarks. A weak boson allows a transformation that powers the sun and shapes radioactive decay. The work is quiet, but the consequences are everywhere. And once you begin seeing bosons this way, as the agents of exchange in a universe built from fields, the next step becomes irresistible. If photons, gluons, and the weak interaction bosons each reveal a different side of how bosonic particles carry the structure of nature, then it makes sense to slow down and look at those messengers more directly, because each one tells us something slightly different about what bosons are capable of doing. Once we start thinking of bosons not just as particles that can share a state, but as the quanta of fields that let the universe do anything interesting between one bit of matter and another, the whole subject becomes much more concrete. Bosons stop feeling like an abstract category in a particle table and start feeling like workers. Quiet workers, certainly, and in some cases spectacularly difficult to observe directly, but workers all the same. They are the messengers of reality in the sense that they are tied to the exchanges through which particles influence one another. And once you look at specific examples, the idea becomes far easier to hold on to. The photon is not the same kind of messenger as the gluon, and neither of them behaves quite like the weak interaction bosons. But together they show how bosons help organize the world at the most basic level. The photon is the friendliest place to begin because light is already familiar. We may not understand it intuitively in all its quantum detail, but at least we have lived with it our whole lives. We know what sunlight does to a room. We know what a lamp does to a page. We know what a laser pointer does to a very serious presentation when somebody at the back of the room is not behaving like an adult. Light is not an exotic fringe phenomenon. It is woven into daily life. That makes the photon one of the most approachable bosons, though approachability and simplicity are not quite the same thing. A photon is the quantum of the electromagnetic field. That means when the electromagnetic field is excited in the right way, the excitation appears as a photon. This is the bosonic particle associated with light, but not only with visible light. The electromagnetic field covers a vast range that includes radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. All of them belong to the same field. All of them are described in quantum terms through photons. So the photon is not a special case reserved for glowing things you can see with your eyes. It is the particle of the whole electromagnetic family. That matters because the electromagnetic interaction is everywhere. It is not some narrow technical phenomenon confined to laboratory devices. It shapes atoms, chemistry, electricity, magnetism, molecular structure, and a good deal of what the visible world feels like. The reason electrons are bound to nuclei in atoms is electromagnetic. The reason molecules form their bonds is electromagnetic. The reason your nervous system functions, your phone lights up, your kettle boils, and your glasses rest on your face instead of drifting dreamily into the wall, is tied at some level to electromagnetic interactions. So when we say the photon is a messenger of reality, that is not grand language for its own sake. It is the boson associated with one of the most basic and far-reaching interactions in nature. One of the photon's most important features is that it has no rest mass. This has profound consequences. Because the photon is massless, the electromagnetic interaction can extend across very large distances. That is why light travels so far. That is why stars can be seen across space. That is why electric and magnetic effects are not confined to microscopic ranges in the same way some other interactions are. The boson's properties shape the force. This is one of the deep recurring themes in particle physics. The character of the messenger helps determine the character of the message. A massless boson gives rise to long-range influence. A massive one behaves differently. There is another thing about photons that makes them very bosonic in a particularly visible way. They can pile into the same state. That is why coherent light exists. In an ordinary bulb, photons are emitted in a comparatively messy and mixed fashion. They still obey bosonic rules, of course, but they are not all coordinated into one neat arrangement. In a laser, they are. Many photons occupy the same state in an organized way, producing a beam of extraordinary coherence. Same direction, same frequency, same phase relationship. That is a direct and very useful consequence of bosonic behavior. If photons were fermions, lasers in the familiar sense would not work because the photons would refuse to share the same state. Every barcode scanner, fiber optic system, precision optical device, and science fiction prop department would have reason to complain. Photons, then, are bosons that do two things at once in the public imagination. They behave like light, which people find charming, and they mediate electromagnetism, which people find harder to picture, until they realize electromagnetism is doing half the work of ordinary life. That is the first messenger. The second is stranger. Gluons are the bosons associated with the strong interaction, and the strong interaction is strong in the most practical possible sense. It is responsible for binding quarks together inside protons and neutrons. Without it, the familiar constituents of atomic nuclei would not exist in their usual form. Protons are not indivisible little pebbles. Neutrons are not either. They are composite objects made of quarks, and quarks are held together by the strong interaction. That interaction is carried by gluons. The name gluon sounds almost suspiciously convenient, as though physicists got tired one afternoon and decided not to overcomplicate things for once. In fact, the name is fitting, because gluons really are part of what holds quarks together. But here the story becomes more complicated than with photons. The electromagnetic interaction is already subtle enough, yet compared with the strong interaction, it can look almost well behaved. One major difference is that gluons themselves carry the relevant kind of charge for the strong interaction. That means gluons can interact with one another. Photons do not carry electric charge in the same way, so the electromagnetic field is comparatively simpler in that respect. Gluons, however, are embedded in a much more self-involved structure. The force carriers are themselves participants in the force. That creates a far richer and more difficult kind of theory. It is one reason the strong interaction does not behave like a stronger version of electromagnetism. It behaves like its own thing. This has several consequences. One is that quarks are confined. You do not find lone quarks strolling about through ordinary matter, pausing perhaps to inspect the fruit aisle before heading home. Quarks are bound into combinations like protons and neutrons, and trying to separate them does not simply give you an isolated quark at the end of the process. Instead, the energy involved can create new particles. The strong interaction becomes stronger in the relevant way as quarks are pulled apart, which is the opposite of how many people instinctively imagine forces behaving. The gluonic field structure is responsible for that peculiarity. Again, the boson is not an optional label. The character of the boson in the field is the reason the force has the personality it does. This also means that gluons are much harder to think about in a simple visual way. A photon can at least be linked in the mind to light. A gluon has no such everyday courtesy. You do not turn on a lamp and see a room full of gluon glow. Their work is hidden inside hadrons. the family of particles that includes protons and neutrons. Much of the mass of ordinary matter, in fact, is tied not just to the bare masses of the constituent quarks, but to the energy associated with the strong interaction binding them together. So gluons are not merely internal stitching, they contribute enormously to the physical reality of matter. The proton is not just three quarks standing politely together, it is a lively, strongly interacting quantum system full of gluonic activity and dynamic structure. That is worth dwelling on because it corrects a very common oversimplification. People often imagine matter as being made of little solid units, stacked inside bigger solid units, like a set of nested dolls if the dolls had studied particle physics and become much less emotionally available. The real picture is far more active. Inside a proton there is motion, field activity, exchange, and quantum complexity. Gluons are part of that inner life. They are the messengers of the strong interaction, but they are also part of the very medium in which that interaction is constantly happening. So photons and gluons already show us two very different faces of bosonic reality. The photon is massless, long-ranged, and linked to the elegant reach of electromagnetism and light. The gluon is also massless in the theory, but because of the nature of the strong interaction and the self-interaction of the gluon field, the resulting force does not extend freely in the same visible way. Instead, it locks quarks together and creates the deep internal binding of hadronic matter. Two bosons, two interactions, two completely different kinds of physical world built from their properties. Then there are the bosons of the weak interaction, which are often discussed less casually because they are much less intuitive from an everyday standpoint. The weak interaction is involved in processes where particles transform from one type into another. It is essential in certain forms of radioactive decay and in the reactions that power stars. Without it, the sun would not shine in the way it does, which would have made the history of life on Earth rather more difficult to organise. So the weak interaction may have a slightly modest name, but its consequences are anything but modest. The bosons associated with the weak interaction are unusual because they are massive. This gives the weak interaction a very short range. Unlike the electromagnetic force, which can reach across enormous distances because its boson is massless, the weak interaction fades rapidly outside very small scales. That is why it does not dominate ordinary large-scale experience in the same way light and electromagnetism do. You're not constantly aware of the weak interaction in the way you're aware of light, heat from the sun, or the electric behaviour of devices. But inside certain particle processes it is indispensable. What makes the weak interaction especially important in the particle world is that it allows changes in identity. It is involved in cases where one kind of quark can transform into another kind, or where particles undergo decays that alter the makeup of matter. This gives the weak interaction a role in the deep bookkeeping of particle physics. It helps regulate how one species of particle becomes another. And because it operates through its own bosons, those bosons become part of the machinery by which the universe is not merely held together, but changed. That is an important distinction. The electromagnetic interaction often feels like a force of arrangement and response. The strong interaction feels like a force of deep binding. The weak interaction feels more like a force of transformation. Those are simplified descriptions but useful ones, and each of them is tied to bosons with different properties, different messengers, different ranges, different kinds of work. There is something almost administrative about this, though perhaps on a more competent level than most administrations we know. Bosons are not all doing the same job. They belong to the same broad family because of their spin and statistics, but within that family they take on very different roles depending on the fields they are associated with. One carries electromagnetism and lets light exist. Another binds quarks into the cores of matter. Others govern particle transformations and radioactive processes. The bosonic category is unified but not monotonous. At this stage it is useful to step back and notice what these examples are teaching us. The boson is not defined by being a force carrier in some vague cinematic sense. It is more precise than that. A boson is the quantum excitation of a field that obeys bosonic statistics. In several of the most important cases, those fields are interaction fields, which is why the bosons function as messengers. But the messenger image works only if we remember that the message is not a sentence written on a card. It is the interaction itself, encoded in the field structure of the theory. Bosons do not run between particles with tiny satchels. They are the quantized way the field transmits influence. Once that settles in, a lot of the apparent mystery becomes less theatrical and more satisfying. Matter does not talk across empty space by magic. Charged particles interact through the electromagnetic field and its photons. Quarks are not glued together by hope and determination. They are bound through the strong field and its gluons. Radioactive transformations are not random little acts of whimsy. They occur through well-defined interactions involving weak bosons. The world is full of events that once seemed separate and descriptive. Bosons help turn them into one connected physical language. There is also a reason these particles matter so much to theory beyond their immediate jobs. They are closely tied to symmetry. The modern description of fundamental interactions rests heavily on symmetry principles, and bosons arise naturally within that structure. The photon is connected to the gauge symmetry of electromagnetism. Gluons emerge from the gauge structure of the strong interaction. The weak bosons come from the framework that unifies electromagnetic and weak interactions at a deeper level. So bosons are not just handy little additions to the model. They are demanded by the mathematical architecture of the theory. The universe, insofar as we can tell, is written in a way that requires these messengers. That does not mean the work is finished. Physics is not sitting back in a deck chair pleased with itself and refusing further correspondence. There are still open questions. Gravity, for example, remains difficult. In a fully quantum theory of gravity, many physicists expect a bosonic particle, sometimes called the graviton, but no direct detection has been made, and the full unification of gravity with the other interactions remains unfinished. So when we speak of bosons as the messengers of reality, we are speaking from within our best current understanding, not from a completed final theory carved in marble and signed off by the universe. Even with that caution, the pattern is extraordinarily powerful. Bosons are the particles that allow fields to act in quantized ways. They help determine how far forces reach, how matter holds together, how particles transform, and how radiation propagates. They are not just one topic among many in particle physics. They are one of the ways particle physics explains why anything influences anything else at all. And yet there is another boson still waiting in the wings, one that is often mentioned with a different tone because its job is not simply to transmit a familiar force between particles in the ordinary way. The Higgs boson is associated with a field that fills space, and the significance of that field lies in how particles interact with it, and thereby acquire an important part of what we call mass. This is one reason the Higgs attracted so much attention. It is not just another messenger standing in line with the photon and the gluon. It points to a field that changes the character of particles moving through the universe. That shift is going to matter next, because after photons and gluons and the weak interaction bosons have shown us how bosons carry influence, the Higgs boson shows us something else entirely. A boson can also be the sign of a field that is not merely passing messages between particles, but setting one of the basic conditions under which those particles exist at all. There is a slightly different mood around the Higgs boson than around photons or gluons, and that is for good reason. When people hear about the photon, they can at least connect it to light. When they hear about gluons, the name itself gives a rough hint that something is being held together somewhere deep inside matter. But the Higgs boson tends to arrive with a different kind of reputation. It sounds grander, more mysterious, and usually a little more burdened by newspaper language than any particle deserves. For years it was introduced to the public in a tone that suggested physics had discovered either the final secret of the universe or an especially difficult celebrity. In truth, the Higgs boson is both more specific and more interesting than the popular slogans made it seem. What makes it special is not simply that it is a boson. Plenty of particles are bosons. What makes it special is the field it is associated with. The Higgs boson is the quantum excitation of the Higgs field, and the Higgs field is not just another field among many passing influences from one particle to another in the style of a messenger. It is a field that fills space. It is there everywhere, quietly present, and certain particles moving through the universe interact with it in a way that gives them mass. That last sentence is one of the most famous in modern physics, and also one of the most easily misunderstood. So it is worth proceeding with some care. The first misunderstanding comes from the title itself, because people often say the Higgs field gives weight. In everyday conversation, that sounds close enough to be harmless, but in physics, weight and mass are not the same thing. Weight is what happens when gravity pulls on mass. Your weight depends on where you are. Your mass does not. If you went to the moon, your weight would change quite a lot, but your mass would not suddenly become shy and decide to stay behind. So what the Higgs field is associated with is mass, not weight. The field helps explain why certain fundamental particles have the masses they do. Gravity can then act on that mass, which is why the everyday sensation of weight enters the story later on. It is a small distinction in casual language, but in physics it matters. The second misunderstanding is the idea that the Higgs field gives all mass to everything in the universe, and that before the Higgs came along, nothing had any physical substance at all. That is not right either. The Higgs field is essential to the masses of certain fundamental particles, including the weak interaction bosons and several matter particles such as quarks and electrons. But when you look at ordinary objects, most of the mass you notice is not simply the sum of bare Higgs-generated masses sitting politely side by side. A great deal of the mass of everyday matter, especially in protons and neutrons, comes from the energy bound up in the strong interaction. The quarks inside those particles do receive mass through their interaction with the Higgs field, but the total mass of the proton, for example, owes a great deal to the dynamic energy of the strong force. So the Higgs field is crucial, but it is not the whole story of mass in every practical sense. Once those confusions are out of the way, the real picture becomes easier to enjoy. The Higgs field is a field that exists throughout space, and some particles interact with it while others do not. That interaction is what gives those particles a resistance to acceleration that we call mass. If the Higgs field were absent, several of the particles we know would behave very differently. The weak interaction bosons would not have the masses they do. Electrons would not have the masses they do. Quarks would not have the masses they do. And because those masses matter enormously for the existence of stable atoms, chemistry, and a universe with recognizable structure, the consequences would be profound. There is a famous popular analogy that compares the Higgs field to a crowd in a room, where one person moves through easily and another is slowed by attracting attention from everyone present. It is a friendly analogy, and it helped many people on first contact, but it can also be a bit too theatrical. The Higgs field is not a room full of nosy onlookers clustering around particles because somebody famous has entered the building. Better to think of it as a real physical field with a non-zero value throughout space, a field that certain particles couple to. The stronger the coupling, the more mass the particle has. The weaker the coupling, the less mass. And if there is no coupling at all, as with the photon, then that particle remains massless. That last point is one of the cleanest ways to understand what the field is doing. The photon does not interact with the Higgs field in the relevant way, and so it has no rest mass. This is why light can travel at the universal speed it does. The weak interaction bosons, by contrast, do interact strongly with the Higgs field, and they are massive. That mass is part of why the weak interaction has such a short range. So once again, the properties of the boson and the field shape the character of the force. The Higgs field is not merely adding decoration, it is determining something basic about how the universe organises interactions. There is also a deeper reason the Higgs field had to enter the theory in the first place. It was not introduced simply because physicists thought the particle list looked a little sparse and could use one more memorable entry. It was brought in because the structure of the electroweak theory, The framework that unifies the electromagnetic and weak interactions at a deeper level required a way for some particles to acquire mass without wrecking the underlying symmetry and consistency of the theory. This is one of those places where modern physics shows its characteristic mixture of strict logic and astonishing weirdness. You do not get to hand particles mass casually without consequences. The theory has to remain mathematically consistent, and the Higgs mechanism provides a way for the field structure to produce masses while preserving the deeper architecture of the model. That phrase Higgs mechanism sounds a bit like a Victorian device, kept in a locked cabinet and only demonstrated on Thursdays, but the core idea is simple enough in outline. The laws governing the field system have a symmetry that would seem to keep certain particles massless, but the state the universe settles into does not display that symmetry in the obvious way. The Higgs field has a non-zero value even in what we call empty space. Because of that background presence, particles interacting with the field acquire mass. The symmetry is not absent in the underlying laws, but it is hidden in the state of the world. This is sometimes described as spontaneous symmetry breaking, another phrase that sounds more dramatic than the quiet mathematical reality behind it. Still, the consequences are enormous. The universe we know depends on this structure. There is a useful everyday comparison here, though it must be used gently. Imagine a perfectly flat dinner table, with a pencil balanced upright on its point in the exact centre. The situation is symmetrical because the pencil could fall equally well in any direction. But once it actually falls, one direction is selected and the visible symmetry is gone, even though the basic setup allowed every direction equally. The Higgs field and its symmetry breaking are not literally that scene, of course, but the idea that the laws can be symmetrical while the chosen state is not. That is the important part. The universe settles into a condition where the Higgs field is present throughout space, and in that settled condition particles acquire mass through interaction with it. This is where the Higgs boson enters. The Higgs boson is the quantum ripple, the particle associated with excitations of the Higgs field. If the field exists, then in quantum theory it can have quanta, and that quantum is the Higgs boson. In that sense, the boson was never merely a decorative trophy for collider physicists. It was evidence of the field. Detecting the Higgs boson meant finding the particle sign that the field mechanism was real. The field itself is the deeper actor. The boson is the telltale excitation that proves the field is not just a convenient idea scribbled in a notebook, but part of the physical structure of the universe. That is why the search for the Higgs boson mattered so much. It was not because physicists had an emotional attachment to collecting named particles like rare stamps. It was because the standard model of particle physics, which had already been stunningly successful, contained this missing piece. The framework worked beautifully in many ways, but the origin of mass for key particles required the Higgs mechanism or something very much like it. The boson was the experimental signature people could look for. When it was finally found, that was not the end of physics, nor did it explain every mystery in one magnificent sweep. But it was a major confirmation that the theory was built on the right kind of foundation. There is something almost funny about the contrast between the scale of the machines involved and the nature of what was being confirmed. Enormous accelerators, huge detectors, vast collaborations of scientists, years of work, and what emerges is the confirmation of a field that quietly fills every bit of space and influences the properties of particles in a way that no one can see directly with their naked eye. Physics has a habit of requiring tremendous machinery to establish the existence of the gentlest sounding ingredients. Still, it is important not to oversell gentleness. The Higgs field may be quiet in the sense that it does not go about making sparks in the living room, but its role is central. Without it, the weak bosons would remain massless in the theory, and the weak interaction would not behave as observed. Electrons without their current mass would not form atoms in the familiar way. Chemistry would collapse into something unrecognizable. Stable matter, as we know it, would not be there to support planets, people, paperclips, or videos about bosons. The field is subtle, but the consequences are not. There is also something interesting in the fact that not all particles interact with the Higgs field equally. If every particle coupled in exactly the same way, the mass pattern of the universe would be flat and dull in a very inconvenient sense. Instead, different particles have different couplings, and this leads to different masses. The top quark, for example, couples very strongly and is correspondingly massive. The electron couples much more weakly and is much lighter. The photon does not couple in the relevant way at all and remains massless. So the Higgs field is not simply an all-purpose mass paintbrush applied evenly over everything. It is a field with specific interactions, and those interactions create the hierarchy of masses among several fundamental particles. That raises one of the lingering questions in modern physics, because while the standard model tells us how the mechanism works, it does not fully explain why the coupling strengths take the particular values they do. In other words, we know that particles get mass from interacting with the Higgs field, but the deeper reason the electron has one mass while the top quark has another is not fully answered by the standard model itself. The numbers are part of the model's input, so the Higgs field solves a crucial piece of the puzzle, but it does not remove every mystery from the room. Physics remains gainfully employed. It is also worth noticing how different the Higgs boson feels from the other bosons we have discussed. The photon is a clean messenger of electromagnetism. Gluons bind quarks. Weak bosons mediate weak processes and particle transformations. The Higgs boson points instead to a background field whose presence changes the conditions under which particles exist. It is not best understood as a simple messenger shuttling between two charged objects. It is better understood as the particle sign of a field that permeates space and helps determine one of the most basic properties of several particles moving through it. That makes the Higgs boson a useful reminder that bosons are a broader family than people sometimes assume. Not every boson plays exactly the same role. What unites them is not one narrow job description, but their spin and their quantum statistics. What distinguishes them from one another is the field they belong to and the work that field does in the structure of nature. In the Higgs case, the work is not mainly long-range communication. It is the setting of mass through pervasive interaction. Another good thing to keep in mind is that the Higgs field does not act like syrup in the crude sense some early explanation suggested. That analogy was meant to convey resistance, but it can give the impression that massive particles are simply slowed down by rubbing against a sticky medium. That is not the right picture. Mass is not ordinary drag. A particle with mass is not constantly losing speed because it is wading through treacle. Mass is a property tied to how a particle responds to force and acceleration. The Higgs field contributes to that property through the structure of the theory. It does not just gum up the works. If it did, the universe would look very different indeed, and nobody would be very pleased with the results. The most satisfying way to think about the Higgs field is as part of the ground arrangement of reality. Empty space is not truly empty in the naive sense. It is structured. It contains fields. The Higgs field is one of them, settled into a non-zero background value. Particles moving through the world are moving through that structured vacuum, and some of them interact with this field in a way that gives them mass. That is a subtler and more powerful idea than the old picture of an empty stage on which particles merely bounce about. The stage itself has properties. Space is not a blank backdrop. It is full of fields, and one of those fields helps determine what particles are like. At this point, the title phrase, "the field that gives weight," can be heard in the gentlest corrected form. Not weight exactly, but the mass that later matters for weight. The distinction is worth preserving because it helps prevent confusion when gravity enters the conversation. The Higgs field does not replace gravity. It does not explain why masses attract gravitationally. It explains a major part of why certain particles have mass in the first place. Gravity then treats mass and energy as sources of curvature in space-time, which is a different story entirely. The Higgs and gravity are not rivals fighting over the same desk. They answer different questions, and perhaps that is one of the nicest things about the Higgs story. It shows how physics advances by learning to ask sharply different questions, rather than mashing all mysteries into one oversized lump. What gives particles mass is one question. Why gravity acts on mass is another. What most of the mass of a proton comes from is yet another. The Higgs field answers one of these with extraordinary success, and in doing so it reveals that the vacuum itself is an active participant in the structure of the world. Once you start seeing fields this way, the universe becomes less like a set of objects arranged in empty space, and more like a layered system of presences, with particles appearing as local excitations, and with background field values quietly shaping what can happen. The Higgs boson is one sign of that deeper architecture. It tells us that bosons are not only the carriers of forces and the makers of coherent radiation, they can also be the visible clues that a field filling all of space is responsible for a property as fundamental as mass, and that opens the next door naturally, because if bosons can gather into the same state, carry interactions, and even signal the existence of a field that shapes the mass of particles, then we're ready to look at one of the strangest things bosons can do when large numbers of them are cooled, quieted, and given the chance to act not as many separate particles, but almost as one. There is a particular kind of strangeness in physics that only appears when something familiar is pushed into conditions so extreme that it stops behaving in the familiar way altogether. Water can do this, metals can do this, light can do this, and bosons, under the right circumstances, do something even stranger. They stop acting like a crowd of separate particles and begin to act as though they are all participating in one shared quantum state. This is the phenomenon called Bose-Einstein condensation, and it is one of the clearest and most astonishing demonstrations of what it really means for bosons to obey different rules from the particles that make up ordinary matter. The first thing worth saying is that the word condensation can be a little misleading if one hears it in the everyday sense. When most people hear condensation, they think of steam turning into water droplets on a cold window or the side of a glass. That is not what is happening here. Bose-Einstein condensation is not merely a gas becoming a liquid. It is not a straightforward matter of particles getting closer together in the ordinary physical sense. It is a quantum transition, a change in how a large number of particles are arranged in the space of possible states. The particles do not simply crowd into the same room, they crowd into the same quantum condition. That difference matters because the whole point of Bose-Einstein condensation is that it reveals the bosonic rule in its most dramatic form. Bosons are allowed to occupy the same state. At everyday temperatures and conditions, that permission does not always produce an obvious spectacle, because thermal motion keeps particles darting about in many different ways. Heat is disorderly. It shakes things loose from neat collective behaviour. But if you cool a bosonic system far enough, if you strip away enough of that thermal agitation, there comes a point where the particles can no longer maintain their individual separateness in the usual way. Their quantum wave nature begins to dominate. Their associated wavelengths overlap. The system stops looking like many little things and starts behaving like one large quantum object. That sentence can sound like the sort of thing science says just to be provocative, but in this case it is literal. A Bose-Einstein condensate is not just an especially tidy gas. It is a state in which a large fraction of the bosons occupy the lowest available quantum state together. Instead of having one atom here, another atom there, each with its own independent quantum identity, the whole collection develops a kind of coherence. It is as though the particles are no longer simply travelling alongside one another, they are participating in a common wave. The idea itself goes back to the early days of quantum theory, which is fitting because it was one of the first hints that the quantum world would not merely tweak classical physics at the edges, but overturn some of its most basic assumptions. Satyendra Nath Bose developed the statistical treatment of photons that later gave bosons their name. Einstein recognized that the same kind of statistical thinking could apply to particles with mass, provided they were bosons. He then predicted that at low enough temperatures a gas of such particles should undergo a remarkable transformation, with a large number of them collapsing into the same quantum state. At the time, this was not something anyone could test directly. It was a theoretical prediction, elegant and strange and almost embarrassingly far from the practical reach of laboratory technology. That gap between prediction and observation remained for decades. Physics often works that way. A theory makes an outrageous claim, everyone squints at it for a while, and then some future generation builds enough machinery to find out whether nature was serious. In the case of Bose-Einstein condensation, the experimental challenge was enormous because the required temperatures are unimaginably low. You're not merely cooling a gas until it feels chilly. You're cooling it to a tiny fraction above absolute zero, the point at which thermal motion is reduced as far as nature allows. Only then does the bosonic tendency to share states rise above the noisy chaos of ordinary heat and become visible on a macroscopic scale. That is what makes the phenomenon so revealing. It is not that bosons become bosons only when cooled. They're always bosons. Photons do not suddenly decide to join the family because the weather has turned. What changes at low temperature is that their distinctive statistical behavior is no longer masked by thermal disorder. The underlying permission to occupy the same state was there from the start. Cooling simply gives it room to take over. To understand why that happens, it helps to recall that in quantum mechanics, particles are not just point-like objects with trajectories. They also have wave properties. The lower the temperature, the lower the typical momentum of the particles, and the more significant their wave character becomes over larger distances. Under normal conditions, the wave descriptions of separate atoms are usually small and distinct enough that the atoms behave like individual members of a crowd. But as the temperature drops, those wave packets spread out. Eventually, the wave descriptions begin to overlap strongly. At that point, for bosons, there is nothing preventing a large number of particles from settling into one common state. In fact, the bosonic statistics favour it. This is where the deeper logic of bosons becomes visible in a way that even common sense can begin to respect. We have already said many times that bosons can share a quantum state. Bose-Einstein condensation shows what that means when the number of particles is enormous and the conditions are controlled carefully enough. It means that quantum mechanics ceases to be merely a theory of the very small in the naive sense. It becomes something that can organize the behavior of a whole cloud of atoms at once. The strange intimacy allowed by bosonic statistics is no longer hidden in microscopic bookkeeping. It becomes the physical reality of the entire sample. That is one reason people sometimes describe a condensate as a giant matter wave. The phrase is helpful so long as it is not taken too casually. A condensate is not one atom blown up to absurd size. Nor is it a blob where all individuality has vanished in some mystical manner. It is a many-particle system in which a huge fraction of the particles occupy the same quantum state, and therefore can be described coherently. The system behaves as a unified quantum entity in ways that ordinary gases do not. If you interfere two condensates with one another, for example, you can observe interference patterns much like the ones familiar from waves. That is not because someone has quietly replaced the atoms with light. It is because the atomic ensemble has entered a shared quantum condition in which wave behavior becomes manifest at the scale of the whole cloud. The first laboratory creation of a Bose-Einstein condensate in a dilute gas was one of the landmark achievements of late 20th century physics. It required extraordinarily delicate control. Atoms had to be trapped, cooled with laser techniques, and then cooled even further through methods such as evaporative cooling, where the most energetic atoms are allowed to escape so that the remaining cloud settles to a lower temperature. There is something oddly domestic about the term evaporative cooling in this context, as though one were simply leaving a pot to simmer less vigorously. In reality, it involved some of the most precise manipulation of atomic systems ever achieved. The target was not merely cold, it was cold enough for individuality, in the quantum sense, to begin dissolving into collective occupation. When the transition happens, the evidence is striking. Instead of the broad spread of momenta expected for an ordinary thermal cloud, a sharply concentrated population appears in the lowest state. It is as though a crowd scattered across a hillside has suddenly flowed down into the same valley and decided to remain there together. Again, that image must not be pushed too hard, because the state is quantum rather than geographical. But the central point is real. A macroscopic number of particles have occupied one quantum state. Nature is no longer dealing with them as many separate thermal atoms. It is dealing with them as a condensate. What makes this mysterious is not just that it happens, but what it tells us about the meaning of particle identity. In daily life, many things can be in the same room while remaining perfectly separate. 100 people in a train carriage are still 100 people, however little elbow room remains. Bose-Einstein condensation is not like that. Here the separateness is not merely physically reduced. It is softened at the level of the quantum description itself. The particles remain particles in an important sense, but the system acquires a unified state that does not respect our old habit of imagining each constituent as living out a private little existence. Bosons, given the chance, trade that kind of individuality for coherence. There is also a useful contrast with fermions. If you try to cool a gas of identical fermions, they cannot all collapse into the same lower state because the exclusion principle forbids it. Instead, they pile up in layers, filling available states one by one. That leads to its own rich and beautiful physics, but not to Bose-Einstein condensation. The condensate belongs specifically to bosons because bosons are the particles for which common occupancy is allowed. This is the point at which all the earlier discussion of exchange symmetry and quantum statistics stops sounding abstract and turns into laboratory reality. Bosons can move as one because bosons are built for shared occupation, in a way fermions are not. That said, nature always finds ways to be slightly more complicated than the neatest version of the story. Some particles that are not elementary bosons can still behave effectively as bosons if they are composite objects with the right total spin. Certain atoms qualify. Even paired fermions can in some circumstances act like composite bosons and enter condensate-like states. This is one of the reasons the bosonic idea is so powerful. It is not merely a label attached to a small set of exotic particles. It is a kind of quantum possibility that can emerge whenever the total structure behaves bosonically. A collection of paired constituents can sometimes achieve a shared state, even if the individual building blocks, taken one by one, would have refused. That is going to matter later when we come to superconductivity and other collective effects. But even without going there yet, Bose-Einstein condensation already teaches the essential lesson. The quantum rules for bosons do not merely affect one scattering event here, or one beam of light there. They can govern the behaviour of an entire macroscopic system. This is what people mean when they say that the quantum world can become visible at larger scales under the right conditions. Not visible in the sense that you can stare into a condensate and watch equations floating about like subtitles, but visible in the sense that the system behaves in unmistakably quantum ways no classical gas ever would. One of the most remarkable features of a condensate is coherence. In an ordinary gas, even a very cold one by everyday standards, each atom behaves more or less independently. There is no single phase linking the whole cloud. No unified matter wave encompasses the lot. In a condensate, coherence extends across the entire sample. This means the atoms are not just close together in state occupancy, but also phase-related in a common quantum description. That coherence is what makes interference experiments possible, and what gives condensates their extraordinary sensitivity and elegance in the laboratory. They are not just cold, they are ordered in a profoundly quantum way. This has led to a great deal of scientific interest, not only because the phenomenon is beautiful, but because it opens practical doors. Bose-Einstein condensates are used to explore precision measurement, quantum simulation, and fundamental questions about many body systems. They allow physicists to create and study quantum behaviour in a form that can be manipulated in ways impossible with most other systems. That is part of the reason the subject feels so alive. It is not merely a historical triumph. It remains a tool for modern research and a window into the collective behaviour of matter under extreme quantum control. Still, the deepest fascination remains conceptual. A condensate forces us to revise what we mean by a collection. We tend to think that a large number of things must become more classical, more statistical, more averaged out, less strange. Bose-Einstein condensation shows that under the right conditions the opposite can happen. A large number of particles can become more deeply quantum together than any one of them looks in isolation. The many do not wash out the weirdness, they amplify it into something shared. That is a very important point because it cuts against one of the most common misconceptions about physics. People often imagine that quantum mechanics is the theory of tiny things, and classical physics is what you get when things become big. That is true often enough to be useful, but not always. If a system is sufficiently coherent and protected from thermal disruption, quantum behaviour can dominate even when the system contains many particles. A condensate is the proof. It is not made of one or two particles doing party tricks. It is a many-particle state whose collective order is irreducibly quantum. There is something almost unsettling about that if you let it sink in. The world we perceive daily is built from matter that, at bottom, obeys quantum laws. Most of the time those laws are hidden by complexity, heat, and interaction with the environment. A Bose-Einstein condensate is one of the places where the quantum order becomes clear again, at a scale large enough to feel less like microscopic rumour, and more like a form of matter with its own personality. It is one of the cleanest demonstrations that bosonic statistics are not just accounting conventions in a theory book. They shape what matter can become. The word mystery in the title is deserved for another reason as well. Even once you understand the mechanism in broad terms, there remains something profoundly strange about the experience of describing many atoms as one coherent state. We can say it carefully, we can measure it, we can calculate with it, but it still presses against the edge of the everyday categories the mind prefers. How many things can be one thing before our language begins to wobble? A condensate does not abolish the many, yet it makes the one newly meaningful. That is a very quantum kind of discomfort, and physics has learned to live with it rather well. There is also a quiet historical beauty in the fact that this state of matter was predicted so early and realised so much later. Bose-Einstein did not have modern laser cooling, ultra-high vacuum systems, magnetic traps, or the enormous experimental sophistication that would eventually make condensates possible. What they had was theory, and theory was enough to see that the statistical life of bosons implied a new state of matter waiting in the wings. Decades later, the experiments caught up. That arc from idea to reality is one of the pleasures of physics. It reminds us that the strange rules of the quantum world are not merely speculative decoration. They wait patiently until we build conditions clean enough to let them speak. If bosons had to be summarized by one image, the condensate might be the most revealing. Not a particle bouncing alone through empty space, not even merely a beam of coordinated light, but a whole cloud of matter entering one shared state. Bosons can do that because bosons are allowed to share. What looks like a minor difference in quantum rule becomes, under the right conditions, a whole new form of matter. That is why Bose-Einstein condensation sits so centrally in the story. It is the bosonic rule made visible as a phase of reality, and once that possibility is on the table, the rest of the landscape opens very naturally. If bosons, or systems behaving effectively like bosons, can enter coherent shared states, then it becomes easier to understand how matter might flow without friction, how electric current might move without resistance, and how some of the most counterintuitive macroscopic phenomena in physics can emerge not from particles staying out of one another's way, but from particles learning, in the quantum sense, to move together. There is a point in this story where bosons stop sounding merely unusual and start looking almost impossible. Up to now, we have seen that they can share a quantum state, that they can act as messengers of force, that they can gather into coherent conditions under the right circumstances, and that the quantum world treats them according to rules very different from the ones that shape ordinary matter. But there is another step, and it is the sort of step that makes physics look less like a set of dry facts and more like a catalogue of carefully verified improbabilities. When bosonic behaviour takes hold on a large enough scale, matter can begin to do things that seem to defy its own usual habits. Liquids can flow without friction. Electric current can move without resistance. Magnetic fields can be expelled from materials in ways that feel almost theatrical. The world, for a moment, stops behaving like the world we grew up with and starts behaving like the quantum world with the volume turned up. This is where superfluids and superconductors enter the scene, and both of them are among the clearest signs that bosonic coherence is not a minor detail in some hidden corner of theory. It is something that can reorganize matter itself. The trick, if one can call it that, is that when many particles begin acting in a shared quantum way, some of the messy ordinary processes that create friction, resistance and dissipation are no longer able to operate as they usually do. The result is a kind of physical elegance that looks almost indecently smooth. Let's begin with superfluidity, because there is something especially unsettling about a liquid that refuses to behave like a liquid. In everyday life, fluids are fussy things. They slosh, they splash, they swirl, they drip, and they lose energy to friction as they move. Pour tea into a cup and it settles. Stir soup and it slows. Water moving through a pipe rubs against the walls and against itself, and some of its energy is steadily wasted as heat. All of that feels ordinary enough that one barely notices it. Friction is such a routine part of existence that its absence can seem less like a possibility and more like a clerical error. A superfluid is a liquid that can flow with effectively no viscosity under the right conditions. Viscosity is the internal resistance a fluid has to flow. Honey has a lot of it. Water has less. A superfluid, by comparison, behaves as though the concept has quietly left the room. Once set in motion in the appropriate way, it can continue with astonishing persistence. It can creep up the walls of a container. It can pass through tiny channels with behaviour that looks less like ordinary liquid motion and more like some very patient kind of quantum insistence. The first time one encounters these facts, one is entitled to suspect that someone has been making things up. But the experiments are real, and the explanation lies in collective quantum behaviour. One of the classic examples involves helium. Helium is already an odd substance in several ways, not least because it remains liquid down to extremely low temperatures under ordinary pressure. Cool one form of helium enough, and it enters a superfluid state. At that point, its behaviour changes dramatically. The liquid no longer fits comfortably into the old everyday description. It begins to display the consequences of bosonic coherence on a macroscopic scale. The key is that the atoms involved can occupy a shared quantum state. Instead of behaving like a disordered crowd of separate particles, they behave coherently. When that coherence dominates, the usual ways in which motion becomes scrambled and dissipated are greatly reduced. Ordinary viscosity depends on all the little chaotic exchanges and collisions through which one part of a fluid drags on another and energy is spread around untidily. In a superfluid, the motion is governed by a collective quantum state, and the tidy coherence of that state changes the rules of the game. The liquid can move in ways that are astonishingly smooth, because it is not acting like a classical jumble anymore. There are few things in physics more satisfying than a phenomenon that sounds like a fantasy, and turns out to be the lawful consequence of a very precise rule. Superfluidity is one of those. It is not a magical exemption from ordinary behaviour. It is what happens when bosonic rules cease to be hidden by thermal disorder and take command of the whole system. The liquid becomes a visible lesson in what shared quantum occupation can do. It also teaches something important about the relation between the microscopic and the macroscopic. We often imagine that the strange features of quantum mechanics should average out as systems get larger, and often they do. But sometimes, under the right conditions, they do not average out at all. They organise. A superfluid is not a single particle misbehaving in a charmingly academic fashion. It is an enormous collection of particles whose shared state produces a new kind of matter. The many do not erase the quantum strangeness. They amplify it into something you can pour, trap, rotate, and study in the laboratory. Rotation, incidentally, brings in one of the more delightful peculiarities. In an ordinary liquid, rotation can occur in a smooth range of ways. Stir it gently or vigorously and the fluid adjusts. In a superfluid, rotation becomes quantized. That means the circulation occurs in discrete allowed amounts rather than any arbitrary value. Instead of a smooth classical whirlpool logic, you get vortices with quantized character, tiny whirlpools of a deeply quantum sort. It is another sign that the fluid is not merely very cold water in an eccentric mood. It is a macroscopic quantum system obeying rules that run deeper than classical hydrodynamics. Now, if superfluidity feels like the liquid side of bosonic miracles, superconductivity is the electrical side, and it is every bit as striking. In an ordinary conductor, electrical current meets resistance. Electrons move through the material, scatter from impurities, vibrate against the lattice of atoms, lose energy, and produce heat. That is why wires warm up. It is why power transmission wastes energy. It is why electrical engineering involves so much practical negotiation with loss, heating, and inefficiency. Resistance is so familiar that it can feel like part of the definition of current itself. A superconductor replies, very politely and very firmly, that it is not. A superconductor is a material that, below a certain critical temperature, allows electrical current to flow with effectively no resistance. Not a little less, not impressively reduced, none in the relevant sense. Once a current is established under suitable conditions, it can persist without the ongoing loss that ordinary conductors suffer. That is already startling enough, but superconductors also do something else remarkable. They expel magnetic fields from their interior in a characteristic way. This is known as the Meissner effect, though in narration it is perhaps enough to say that the material does not merely conduct perfectly, it enters distinct physical state with its own magnetic behaviour. A superconductor is not just a very good wire, it is a new phase of matter. At first glance this can seem puzzling, because the charge carriers in a metal are electrons, and electrons are fermions. Fermions, as we have discussed at some length, do not get to pile into the same state the way bosons do. So how does a phenomenon so clearly tied to coherent shared behaviour emerge from a sea of fermions? The answer is one of the most elegant twists in condensed matter physics. Under the right conditions, electrons can pair up. These pairs are not elementary bosons in the sense that photons are bosons, but the pair as a whole can behave effectively like a boson. And once you have something bosonic, the door to shared occupancy opens. These are often called Cooper pairs, and the idea is one of those marvellous examples where physics takes what seems impossible and makes it inevitable. Two electrons normally repel one another because they carry the same electric charge. Left to their own devices, they are not natural dancing partners, but in a crystal lattice at low enough temperatures, the interaction between electrons and the vibrations of the lattice can create an indirect attraction that overcomes this repulsion in the relevant way. The electrons pair. Each pair has a combined quantum character that allows it to behave effectively as a boson. Then vast numbers of such pairs can occupy a shared state coherently. This is the crucial step. Superconductivity is not simply about the electrons moving very neatly. It is about effective bosonic behaviour emerging from paired fermions. Once these pairs form and condense into a coherent state, the current they carry is no longer just a classical flow of separate charges bouncing through a messy material. It is a collective quantum motion. The usual scattering processes that create resistance are suppressed because disturbing the coherent state is not as simple as nudging one electron off course. The system behaves as a whole. That is why the bosonic theme matters so much here. Bosons, or effective bosonic composites, can occupy a common state. That shared state brings with it coherence. coherence changes transport, and suddenly, electricity can move without resistance. What sounds at first like a technical classification of particle families ends up determining whether matter can support one of the most extraordinary electrical phenomena ever observed. There is something wonderfully subversive about that. Ordinary materials teach us to expect friction and loss. Bosonic coherence teaches us that those expectations are conditional, not absolute. Remove enough thermal agitation, establish the right kind of collective state, and matter will reveal a hidden capacity for perfection that daily life almost never shows. The current does not trickle more efficiently. It stops wasting energy in the familiar way altogether. Superconductors have also made possible some of the most dramatic technological tools in modern science and medicine. Strong magnetic fields for imaging, particle accelerators, precision measurement devices, and many forms of quantum technology rely on superconducting behavior. In other words, this is not merely one of those beautiful physical ideas that remain locked in a display case for specialists to admire. It has practical force. Bosonic coherence has become engineering. There are, of course, complications. Not all superconductors behave identically. Some operate at temperatures so low that one begins to feel personally offended on behalf of room temperature. Others, the so-called high-temperature superconductors, operate at temperatures that are still cold enough to make ordinary comfort irrelevant, but are significantly higher than the earliest known cases. The exact mechanisms in some of these materials remain an active area of research, which is physics, for we understand a great deal, but not yet everything we would like. Still, the central lesson remains. Superconductivity is a collective quantum state, and bosonic behavior is at its heart. Superfluids and superconductors are often discussed together because they are sibling expressions of the same deeper idea. In both cases, a system enters a phase where coherence dominates. In both cases, the ordinary disorderly routes by which energy is dissipated are radically altered. In both cases, the system behaves less like an assembly of independent particles and more like a unified quantum entity. The details differ, certainly. A fluid flowing without viscosity is not the same as a conductor carrying current without resistance. But the family resemblance is unmistakable. These are bosonic miracles in the sober scientific sense. They are miracles only because everyday intuition had very poor expectations. And the miracles do not stop there. Once physicists realized that collective bosonic states could reshape matter so dramatically, whole new categories of behavior came into view. There are superfluid phases in ultra-cold atomic gases, coherent quantum states in optical systems, paired states in nuclear and astrophysical contexts, and exotic condensates that appear in settings where one would not have guessed bosonic physics could dominate so strongly. Even systems of quasi-particles, which are not fundamental particles in the deepest sense but effective excitations in materials, can display bosonic condensation and coherence. Physics, having found one way for the world to behave strangely, rarely stops at one. This is also the right place to notice how much the word boson has expanded from where we began. At first, it may have seemed like merely a particle family name. Then it became a clue to force-carrying fields. Then it became a key to the Higgs field and mass. Now it is the gateway to entire phases of matter in which large systems behave as one. A boson is not just a particle that ignores the exclusion principle. It is the possibility of coherence made fundamental. That is the real thread running through everything. Bosons allow collective occupation, and collective occupation allows collective phenomena. Once enough of a system is gathered into the same quantum state, matter starts showing us abilities it usually keeps hidden. There is something almost architectural in this. Fermions are wonderful at building structure through enforced distinction. They create layers, shells, spacing, and the orderly stubbornness of matter. Bosons are wonderful at creating structure through shared state. They create fields, coherence, and the possibility that many particles can act as one. The universe appears to need both methods. One builds the walls, the other teaches the walls to sing. It is tempting to ask whether these coherent phases are somehow closer to the true nature of matter than everyday states are. That may be putting it too grandly, but the question contains a worthwhile instinct. Ordinary conditions hide a great deal of quantum order under heat, collisions, noise, and complexity. Superfluids and superconductors reveal what becomes possible when that noise is suppressed and collective organization is allowed to emerge. They are not more real than the ordinary world, but they are more revealing of the quantum rules underneath it. They show us what matter wanted to do all along, if only daily life would stop interrupting. This is one reason low-temperature physics has such a special place in the broader story of nature. Cooling a system is not just a matter of making it sluggish, it is often a way of removing distraction. Thermal motion is a kind of chatter, and when the chatter quiets down, deeper patterns can become audible. Bosonic systems, in particular, are waiting for that quiet. Give them low enough temperatures and the chance to share a state, and suddenly the hidden grammar of the quantum world starts speaking in macroscopic sentences. That speech can sound almost absurd when translated back into everyday language. A fluid climbs a wall, a current flows forever, a magnet levitates above a superconducting track because of flux pinning and field exclusion. A cloud of atoms interferes with another cloud as though matter itself had become a wave choir. All of this would sound like exaggeration if it were not so well established, but the experiments are there, the theory is there, and the explanation points again and again to the same bosonic permission that seemed so modest at the start. Bosons can share a state. That is all. And from that tiny sentence comes an entire world of impossible-sounding matter. Perhaps the most important thing these phenomena teach is that resistance and friction are not as fundamental as they feel. We often treat them as built into the essence of motion itself, yet they are contingent outcomes of many body disorder, scattering, and the failure of coherence. Where coherence wins, resistance can vanish. Where bosonic order dominates, viscosity can disappear. The universe has hidden within it the possibility of motion without waste. It just does not offer it cheaply. And that leads very naturally to the deeper conceptual layer still waiting underneath all of this. Superfluids and superconductors are not random curiosities. They're consequences of symmetry, order, collective states, and the structure of the quantum world itself. Once matter begins acting as one, questions about what is being ordered and what symmetries are being revealed or broken start to move to the center. In other words, bosonic miracles do not merely astonish. They point toward a deeper logic, one in which the universe uses order and symmetry to decide how its most extraordinary states can exist at all. By this point, the boson has worn several different faces. It has appeared as a particle that can share a state with others of its own kind. It has appeared as the quantum of light. It has appeared as a carrier of interaction, a clue to the Higgs field, and the hidden permission behind condensates, superfluids, and superconductors. That already gives it a rather full working week. But there is still a deeper thread running through all of this, and it is the thread that helps explain why bosons so often seem to arrive wherever physics becomes less about separate objects and more about structure itself. Bosons reveal something profound about order, symmetry, and the quantum world, because they are tied not only to what things are, but to how reality organizes itself at the deepest level. That may sound grander than necessary, so it is worth taking it slowly. Order is one of those words that people use very casually until science gets hold of it and refuses to let it remain vague. In ordinary life, order means neatness, arrangement, things in their place. A tidy desk is ordered, a row of books is ordered, a sock drawer with matching pairs is, in theory, ordered, though in practice the universe remains morally ambiguous on that point. In physics, order usually means something more precise. It means that a system displays some consistent pattern, alignment, or regularity that is not present in a more disordered state. That pattern can be obvious, like atoms arranged in a crystal, or it can be more subtle, like a shared quantum phase extending across a whole condensate. Bosons matter here because their willingness to occupy the same state makes certain kinds of order possible on a scale that would be much harder or impossible for fermions alone. When many bosons gather into one state, what emerges is not just a crowd but a pattern. Coherence itself is a kind of order. A laser is ordered light. A Bose-Einstein condensate is ordered matter in a quantum sense. A superfluid is ordered motion. A superconductor is ordered electrical behaviour. None of these things are tidy in the household sense, but all of them reveal that nature can create collective regularity by allowing many particles to participate in one common arrangement. This is already a striking lesson, because it shows that order in physics is not always about separation and spacing. Sometimes it is about unification. We are used to the idea that structure comes from keeping things apart. Bricks stay in their places, letters stay in order, people remain in their own seats unless the train is unusually busy. Fermions support that kind of thinking because their exclusion rule enforces distinction. Bosons show a different route. They support order through sameness, through common occupation, through collective alignment. The result is that the quantum world has at least two very different ways of building reality. One through disciplined separation, the other through disciplined togetherness. That word discipline matters. Bosonic order is not chaos disguised as friendliness. When bosons gather into the same state, they do so according to very strict quantum rules. This is not a free-for-all. A condensate is not a jumble. A laser beam is not a mess. A superconductor is not confused. In each case, the common state is highly organized. The particles are not simply crammed together, they are coordinated. The bosonic permission to share becomes the basis for a new kind of large-scale regularity. And regularity leads naturally to symmetry, because in physics, symmetry is one of the main ways we describe what remains unchanged when something else changes. That sounds abstract, but it is really one of the simplest and most powerful ideas in science. A circle is symmetrical because it looks the same after certain rotations. A law of physics is symmetrical in a deeper sense if it remains the same under some transformation, perhaps a shift in position, a shift in time, or a change in the internal mathematical description of the fields involved. Symmetry tells us what the universe does not care about. It tells us which changes are superficial and which changes are real. Once modern physics discovered how central symmetry is, bosons began showing up with suspicious regularity in all the right places. That was not an accident. The bosons associated with the fundamental interactions are deeply linked to symmetry principles. The photon is tied to the symmetry structure of electromagnetism. Gluons arise from the symmetry structure of the strong interaction. The weak interaction bosons emerge from the electro-weak framework. Even the Higgs field enters the story through a symmetry that is hidden by the state the universe settles into. Bosons, in other words, are often the visible or measurable expressions of deeper symmetries built into the quantum world. This is one reason bosons can feel both concrete and elusive at the same time. On the one hand, they are particles. They appear in experiments. They can be detected, inferred, and studied. On the other hand, they are not merely little objects flying about independently. They are often the quanta of fields demanded by symmetry. That makes them less like random items in nature's inventory, and more like necessary consequences of how the world is structured. The photon is not just a happy little accident of electromagnetism. It belongs there because the field and its symmetry require a bosonic quantum. The same broad logic holds for the other gauge bosons. The messenger is part of the architecture. That word architecture is worth keeping for a moment because it captures something important about the quantum world. We often imagine physics as a list of ingredients. Here are the particles, here are the forces, here are the laws. But the deeper picture is more like a building whose stability depends not only on the pieces, but on the pattern according to which the pieces fit together. Symmetry is part of that pattern. Order is part of that pattern. Bosons show us where the building is holding itself together through shared quantum behaviour and through field structures that reflect deeper invariances. This becomes especially clear in phases of matter where symmetry is not merely present in the laws, but transformed in the state of the system. We touched on this with the Higgs field. The laws can possess a symmetry, even if the state the system settles into does not display that symmetry openly. That is one of the most fertile ideas in modern physics. A system may begin with a range of equivalent possibilities, but once it chooses one configuration, the visible order changes. Something similar happens in many condensed matter systems. A superconductor, for example, does not merely conduct well. It enters a phase with a distinct kind of order. A condensate is not merely cold, it possesses a coherent macroscopic state. The world is full of cases where new order emerges because the system settles into a configuration that reveals some structure while hiding others. Bosons are especially good guides to this kind of emergence because their statistical behaviour makes collective states possible. Emergence is another word that tends to be used too casually unless watched carefully. In physics, it means that large systems can display properties not obvious from the behaviour of individual components alone. Wetness is not something one molecule possesses. It emerges from many molecules together. A traffic jam is not a property of one car. It emerges from many cars in relation. In much the same way, coherence, condensation, superconductivity, and superfluidity emerge from many bosons, or effectively bosonic pairs participating in shared states. The individual particle does not carry the whole phenomenon around in its pocket. The phenomenon arises when the particles act together. That tells us something rather deep about the quantum world. It is not just a place where tiny things obey odd rules one by one. It is a place where collective behaviour is built into the rules from the beginning. Bosons make that especially visible, because their common occupancy can turn many particles into one organised state. If fermions teach us the logic of exclusion and layered structure, bosons teach us the logic of coherence and emergent order. Together they reveal that the quantum world is not smaller than the everyday world in any simple sense. It is richer. It contains more possible forms of organisation than common sense tends to allow. There is also an important connection here to information. Ordered systems carry information in a more structured way than disordered ones. A laser beam, because it is coherent, is not just brighter than random light in some narrow sense. It is more ordered. That order makes it useful. It can be focused precisely. It can carry signals. It can measure distances and encode data. A superconducting state is not just a weird electrical curiosity. Its order makes possible forms of stability and precision ordinary conductors cannot provide. Bosonic order is not merely elegant, it is usable. It gives the quantum world ways of storing, transmitting and expressing regularity. This is one reason bosons matter so much in quantum technologies. Whenever physicists and engineers try to make use of quantum coherence, bosonic behaviour or bosonic-like collective states often appear at the centre. That is because coherence is a form of order, and bosons are the family of particles for which shared occupation and collective phase relationships can be maintained in especially powerful ways. The same features that make them strange in theory make them valuable in practice. At the philosophical edge of the subject, bosons also force us to rethink what individuality means in nature. We are very fond of individuality. We build law, literature and dinner party seating plans around it. But the quantum world is not obliged to treat individuality as sacred. Identical bosons are not merely very similar. They are fundamentally indistinguishable in a way that reshapes what counts as a configuration of the system. That is part of why their statistics differ from classical objects, and that indistinguishability in turn is part of why large-scale coherence becomes possible. Bosons reveal that at the deepest level, nature is not always made of little private stories happening side by side. Sometimes it is made of shared states in which the distinction between one occupant and another matters less than the collective pattern they form together. This is not to say that individuality disappears everywhere. The world we live in remains richly structured by objects, boundaries, and distinguishable things. But bosons remind us that this is not the whole story. Beneath the visible layer is a level where relations, symmetry, and shared occupancy can be more fundamental than separate objecthood. In some contexts, what matters most is not who is where, but what common state the system occupies. That is a radically different way of thinking about reality, and it is one reason quantum mechanics never quite settles down into mere familiarity, no matter how many times you read the textbooks. Bosons also reveal something about simplicity. Many of the most powerful ideas in physics turn out not to be long catalogues of detail, but short principles with enormous consequences. Symmetry is one of those. The distinction between fermions and bosons is another. The permission for identical bosons to share a state sounds almost trivial when said quickly, yet from that permission come lasers, condensates, superfluidity, superconductivity, and the quantum structure of force-carrying fields. A small difference in rule produces a huge difference in world. That is the sort of thing physics is particularly good at uncovering. It tells us that reality can be governed by concise principles, whose consequences only become obvious after long effort, and a great many very serious people standing around detectors. There is another subtle lesson here too. Order in physics is often purchased at the price of fragility. A coherent bosonic state is powerful, but it is also vulnerable. Thermal noise, environmental disturbance, and random interactions can disrupt it. That is why so many bosonic miracles require low temperatures or carefully controlled conditions. Coherence is not impossible, but it is delicate. Symmetry and order are not always the default outcome. They must sometimes be protected. That balance between possibility and fragility is part of what makes the quantum world feel so alive. It is not a rigid machine in which every elegant state automatically appears. It is a landscape of possibilities, some of which emerge only when the conditions are right. And yet, once they do emerge, they can tell us something universal. A condensate in a laboratory, a superfluid phase in helium, a superconducting circuit. These are not just local oddities. They are windows into the same deeper logic. They show that the laws of the quantum world permit order through common state. They show that symmetry can govern not only equations on paper, but the behaviour of actual matter. They show that bosons are not just particles on a list, but signs of how the universe allows collective structure to form. This broader view also helps us avoid a common mistake, which is to think of bosons as the weird particles and fermions as the serious ones. Bosons are no less serious. In some ways, they are the particles through which seriousness enters the room. They are tied to the fields that mediate interactions, the symmetries that organise theories, the coherent states that produce new phases of matter, and the hidden order that emerges when conditions allow. If fermions build the persistent skeleton of matter, bosons help reveal the patterns according to which that skeleton can move, interact, and organise itself. That is why bosons point beyond themselves. Once you follow them far enough, they stop being just a topic and become a method of seeing. They teach you to ask not only what the ingredients are, but what symmetries constrain them, what order can emerge among them, what fields connect them, and what happens when many of them are allowed to share one state. In that sense, bosons reveal the quantum world not as a zoo of bizarre particles, but as a structured domain in which order, symmetry, and collective behaviour are woven together from the ground up. And after all of that, we arrive at a very simple-sounding question that turns out to be the hardest one of all. Once we strip away the headlines, the metaphors, the examples, the force carriers, the condensates, the fields, and the miracles, what is a boson really? Not just what does it do, and not just where does it appear, but what kind of thing is it in the deepest physical sense? That is where the whole path has been leading, because once you have seen what bosons reveal about the structure of the universe, you are finally in a position to ask what the boson itself truly is beneath all the roles it plays. After all this time spent circling the subject from different angles, from light and forces to condensates and superconductors, from the Higgs field to the strange willingness of identical particles to gather into one state, we arrive at the question that sounds simplest and turns out to be the hardest to answer cleanly. What is a boson really? Not just what it does, not just which experiments detect it, not just which famous particle carries the name, but what sort of thing it is in the deepest physical sense. The reason this question is hard is that physics is rarely satisfied with the kind of answer our everyday minds instinctively want. We like nouns that feel solid. We like definitions that point to an object the way one points to a teacup and says that is a cup. Bosons do not cooperate with that habit. They are real, certainly. They are measurable, indispensable, and woven into the structure of the world. But they are not little pebbles of meaning sitting about in empty space waiting to be identified. To understand what a boson really is, we have to let go of the older picture of matter as tiny hard objects first and everything else second. We have to think in terms of quantum fields, shared states, symmetry, and the peculiar fact that nature seems to divide its particles into two great families with two very different ways of existing. So let us begin with the plainest version. A boson is a quantum particle with integer spin that obeys Bose-Einstein statistics. That is the formal answer, and like many formal answers in physics, it is both completely correct and not nearly enough on its own. It tells us how bosons are classified, but not why they matter or what that classification really means. The phrase integer spin sounds technical. The phrase Bose-Einstein statistics sounds like the sort of thing one encounters at the end of a chapter, just before deciding to make tea and reconsider one's life choices. But behind those phrases is the whole secret. A boson is the kind of particle for which identical members of the same species can occupy the same quantum state. That is the heart of it. If fermions are the particles that enforce quantum individuality by refusing identical overlap, bosons are the particles that permit shared existence. They are the particles for which common occupancy is lawful. They are the particles for which coherence can build rather than being forbidden at the door. This is why photons can pile into a laser beam. It is why bosonic atoms can form a Bose-Einstein condensate. It is why coherent quantum states can emerge on large scales. The boson is not merely a particle with a different badge. It is a particle for which the universe allows togetherness. That word togetherness can sound suspiciously sentimental in physics, so it is worth keeping it disciplined. Bosons do not huddle because they are lonely. They do not prefer company in the human sense. They obey a mathematical structure in which exchange leaves the joint quantum description in a form that permits overlap and reinforcement. The result is what we have been calling bunching, coherence, and shared occupation. But the underlying point is not emotional. It is structural. A boson is a particle whose identity in the quantum world is compatible with collective state. Even that, though, is not the whole answer, because a boson is not just a member of a statistical family. In modern physics, bosons are usually understood as excitations of fields. This matters enormously. The old image of particles as tiny separate objects moving through empty space is useful for some rough purposes, but it is not deep enough. The modern view begins with fields. The electromagnetic field is fundamental. The fields associated with the strong interaction and the weak interaction are fundamental. The Higgs field is fundamental. Particles are then the quantized excitations of those fields. A photon is a quantum of the electromagnetic field. A gluon is a quantum of the strong field. The Higgs boson is a quantum of the Higgs field. In that sense, a boson is not just a thing. It is an event in a field, a localized quantum excitation, a unit in which a field appears as a particle. That makes bosons at once stranger and more intelligible. Stranger because it takes us farther from the old little billiard ball picture. More intelligible because it explains why bosons so often appear as carriers of interaction and as signs of deeper structure. If the world is made of fields, then the quanta of those fields are how the fields become observable. Bosons are often the visible grain of invisible structure. They are how the underlying fields of nature show up as particles in experiments and as influence in the world. This is one reason photons feel so central. The photon is not just a tiny packet of light. It is the electromagnetic field in its quantum form. The same boson that makes light possible is also tied to the electromagnetic interaction between charged particles. That is not a coincidence. It is one and the same field structure revealing itself in two connected ways, and the same logic holds more broadly. Bosons are often the places where the universe stops being a list of objects and starts looking like a network of fields in motion. So if one were to answer the question very carefully, one might say that a boson is a quantum excitation of a bosonic field, a particle whose spin and exchange behaviour place it in the family that allows identical quanta to share a state. That is closer to the full truth. But even this still sounds a little like we're reading the label rather than opening the box. Perhaps the better way to understand what a boson really is, after everything we have covered, is this. A boson is nature's way of making collective order possible at the quantum level. That is not a textbook definition, but it is one of the deepest truths about them. Fermions make stable matter by refusing identical occupancy. Bosons make coherence, mediation, and common state possible by allowing it. The universe needs both. It needs particles that build structure through separation and particles that build structure through sharing. Bosons belong to the second mode of reality. That is why they appear wherever the world seems to be acting as one. In a laser, countless photons align into a coherent beam. In a condensate, atoms share one quantum state and behave like a giant matter wave. In a superfluid, motion becomes smooth because the liquid is governed by a collective quantum state. In a superconductor, paired electrons behave effectively like bosons and move in a coherent way that eliminates ordinary resistance. In every case, the bosonic character is not a side note. It is the permission slip for the phenomenon. It is also why bosons are so deeply tied to symmetry. The modern theory of fundamental interactions is built on symmetry principles, and the fields demanded by those symmetries have bosonic quanta. So a boson is often not just a particle in the inventory. It is the quantum expression of an underlying invariance in nature. The photon belongs to the symmetry structure of electromagnetism. Gluons belong to the symmetry structure of the strong interaction. The weak bosons belong to the electroweak framework. The Higgs boson points to a field whose background presence reshapes the masses of particles. Bosons, then, are often the places where deep mathematical order in the laws becomes physical reality. There is something satisfying about that because it means bosons are not arbitrary. They are not little complications added by theorists who felt the universe was becoming too easy to explain. They are required by the logic of the world as we currently understand it. When physics found that certain symmetries seemed to govern the interactions of nature, bosons emerged as part of that structure. When quantum statistics demanded two great families of particles, bosons emerged as one of those families. When experiments examined light, nuclear structure, low-temperature matter, and high-energy collisions, bosons kept turning up exactly where the theory said they should. And yet, for all this, the boson remains hard to picture, because it resists becoming one simple image. A photon is not a gluon. A gluon is not the Higgs boson. A condensate atom is not the same sort of thing as a weak interaction boson. What unites them is not one shared everyday appearance, but one deep mode of quantum existence. They all belong to the family for which integer spin and Bose-Einstein statistics go together. They all belong to the side of reality where common occupancy is permitted. They all belong to the kind of field quanta that can give rise to coherence, mediation, and collective order. This is also why the question what a boson really is cannot be answered by saying it is a force carrier and stopping there. Many important bosons do mediate forces, but that is not the entire category. The Higgs boson does not fit neatly into the public image of a messenger shuttling between two particles in the same way the photon does. Composite bosons in condensed matter systems do not either. The better answer is broader. A boson is a particle type defined by its spin and quantum statistics, and because of those properties, bosons often appear as field quanta, force mediators, and the basis of coherent many-particle states. The family is unified by rule, not by one narrow job. There is also a very quiet philosophical shift hidden in all this. Bosons teach us that the universe is not built only from objects. It is also built from possibilities of relation. Matter does not just sit there being itself. It interacts, exchanges, coheres, transforms, radiates, and organizes. Bosons live in that layer of reality. They're often the particles of relation rather than the particles of occupancy in the old solid sense. The photon lets charges interact. The gluon lets quarks remain bound. The weak bosons let particle identity change in certain processes. The Higgs boson reveals a field that helps set mass itself. Bosons are not always the furniture of the world. Very often they are part of what makes there be a room at all. That may be why the boson feels so elusive to common sense. We evolved to think in terms of objects first. Rock, tree, animal, chair. Our brains are good at things that stay where they are and complain if something else tries to occupy the same place. We are, in that sense, creatures of the fermionic worldview. Bosons ask us to think instead in terms of fields, coherence, and allowed overlap. They ask us to accept that the deepest structure of reality is not only about what is where, but about what can be shared. That is a difficult shift, but once it lands, the whole quantum world becomes less like nonsense and more like an unfamiliar but consistent language. One could even say that a boson is nature's answer to the question of how many can be one without ceasing to be many. That is not the sort of sentence you would print on a laboratory manual, but it captures something real. Bosons preserve multiplicity while permitting common state. A laser beam contains many photons, but they act coherently. A condensate contains many atoms, but they share one quantum condition. A superfluid contains a vast number of particles, but its behavior reflects a unified order. Bosons occupy that fascinating territory where individuality is not destroyed, but coordination becomes more fundamental than separateness. At the same time, one should resist making bosons sound mystical. Physics does not need incense. What makes bosons remarkable is not that they evade explanation. It is that their explanation is so precise and yet so unlike what everyday thought prepared us for. The rules are sharp. The experiments are repeatable. The theory is mathematically disciplined. The wonder comes not from vagueness, but from exactness. Nature really does distinguish between particles that must remain distinct and particles that may merge into one state. Nature really does use bosonic fields to mediate interactions. Nature really does permit coherent matter and light because bosons obey the rules they do. The surprise is not that physics lacks an answer. The surprise is that the answer is both so strange and so thoroughly supported. And that may be the final thing a boson really is. It is a reminder that the deepest truths of the universe are often not the ones common sense would have voted for. If you asked ordinary intuition how particles ought to behave, it would likely choose something very fermionic. Everything separate, everything labelled, everything taking its turn. Bosons reveal another possibility. They reveal that reality also allows common state, shared identity in the quantum sense, and coherent order on scales from light beams to liquids to whole fields filling space. They reveal that the world is not only built by exclusion, but also by participation. So in the end, a boson is not merely the particle that does not follow the usual rules. It is the particle that reveals the usual rules were never the whole story. It is the quantum of a field. It is the member of the family with integer spin. It is the particle for which Bose-Einstein statistics allow shared occupancy. It is the basis of light, of several fundamental interactions, of the Higgs field is observable ripple, of condensates, superfluids, and superconductors. It is one of the main ways nature creates order not by keeping things apart, but by letting them move together. And perhaps that is the gentlest way to leave the subject. The boson turns out not to be one strange exception in physics, but one of the basic shapes reality can take. Matter has its quiet stubbornness. Fields have their restless reach. Fermions give the universe structure through boundaries. Bosons give it structure through coherence. Between them, the world becomes what it is. A place of objects, yes, but also of interactions. A place of separate things, yes, but also of shared states. A place where light can stream, particles can bind, currents can flow forever, and a field filling all of space can help determine what mass means in the first place. And once you begin to see bosons that way, not as obscure particles hidden in the fine print, but as one of the fundamental ways the quantum world organises itself, the word stops sounding so technical. It starts to sound more like what it has been all along. A name for one of the universe's deepest habits.